Hey guys, welcome back for the very last time. This is the final gym video, the gym final, end to the series, end to the quarter, which I hope many of you are looking forward to, as am I. It's been a very long and tough quarter. Time to finish out great. So we're going to go ahead and in this video go through the two midterms. I've written the final midterms. Some thoughts on these midterms, as you'll see. To be honest, I try to model it from what I can remember from when I took it. When I took 118B, it was about 2, maybe 3 pages of MC. MC is very, very old material, heavy. Right? All the old stuff kind of shows up. So I try to remember some of the questions that I could remember from my final, or just whatever I could remember from hearing from other people on their finals. So usually the beginning of it is a marathon of MC, which is a lot of old material, some new material too, right? It's not completely just old material, but majority of that old material is going to show up in this first section. Okay. Second section is usually some amount of MC. From what I remember, I only remember a full page when I took it. So I think it's the same for you guys. Just a full page of MC. And PTP, not MC, a full page of PTP. I imagine it'll be the same for you guys as well. If not, just more questions, but that's not too bad, right? This is a bulk of the new material, right? The start of the new material really shows up where you're expected to reproduce or show that you've learned the new stuff, right? There might be a little old material here and there, some concept questions, like a couple of these incorporate old concepts, and I think not really on this end, but definitely on this end, a couple of these reactions enforce old concepts, but definitely expect that. 2 mechanisms just really can be anything. Hopefully, I think someone said, I take that back. Someone said it'd be new material. That's why I wrote these to be newish material. So all new materials, that's great. Synthesis can hit all parts of the course. So I've written questions that, I haven't seen these questions before, so don't worry. It's not like I'm taking these questions from old material and you guys are thinking, oh my God, this is the thing. I'm just taking all the possible transformations you can think of that apply to old material that you can use in the end. So these are, sort of the culminations that I think if you can do these 6 syntheses, you'll be pretty set for the final. Okay. Last but not least, everyone's favorite portion, the NMR. We'll go over this very, very last. Just to go over tricks, right? We're not aiming to fully finish this, especially since I know this is going to take at least 2.5 hours, this video probably. Hopefully just 2, but possibly 2.5. Cool. All right. Now, I know usually in these videos, I take a chunk of time in the beginning to kind of walk through everything, talk about all the reactions. That was midterm 1, right? Because I had the time. Midterm 2 kind of had to, section off time to certain material and go over that. To be completely honest with you guys, there's just way too much stuff to cover. There's no way I can finish it within an hour and a half. And I want to be able to go through the exam and, also make it useful for those that need to speed run the video, right? They need to put this on times 10 and watch this so that it ingrains in their brains. So what I'm going to do instead is I'm going to go ahead and work through the exam, but we're going to go through the exam by doing questions and talking about the concepts alongside the questions. So that way we're getting the exam done while reviewing material. Something that probably I should have done back in the past. It's kind of harder with the past material, but it's a little bit easier with this one. But we'll go through the material, hit the concepts, talk about other things, and I'll also keep a list of all the extra questions we talk about, and I'll throw them onto another document, put it up, so that for those of you that, again, just have to speed run the video, don't have the time to write down or look at everything, at least there's a document that lists out the other things that I said, or at least reactions I talked about. Okay, so I know you guys love hearing me talk, go OChem for hours. Who wouldn't, right? But today is just not that type of night. We're just gonna have to go ahead and get work through the material and get to some point. So I will make my way through the material in a way. So we're not really going to start at A. We're actually going to start at H. But I'm going to make my way through the material in a way that kind of mimics the chapter setup, so that we're hitting all the questions in the order that they show up, and so the concepts can kind of neatly kind of slide into each other. And so again, it's like a review while we're doing the exam. So it kind of benefits both sides here. Cool. All right. Well, with that said, with the plan set out, hopefully everyone's happy with it. Let's just get right into it and start the gym final review, right? Last time we're going to be doing this, so sad. I am. It's okay if you're not, but I am. Cool. All right. So starting with H, this is a ketone reaction with looks like an alcohol and acid. Right? Recall that carbonyls are electrophilic compounds, right? We have two flavors of them. We have the ketone and we have the aldehyde. And generally speaking on these guys, in terms of reactivity, right, aldehyde's way more reactive. Right, and that's just a function of the fact that if we look at the kind of groups that we have around these carbonyls, ketones have two of these R groups that can donate inductively, right, which increase stability. There's a name for this, starts with an H, right? Hyperconjugation. Right, we have an sp3 center donating electrons into an sp2 center. That's a hyperconjugated interaction, right? Whereas the aldehyde only has one. So stability is going to be lost, at least relative to the ketone. Okay. Generally speaking, aldehydes more reactive than ketones. Are there anything more reactive than aldehydes? For sure, right? We have carbonyls with donating effects. What about carbonyls with withdrawing effects? I mean, we learned all about these EWGs. So you can imagine having an EWG here, which pulls out, whether it's inductive or by resonance, going to be incredibly, incredibly reactive. Okay. So in fact, actually, the very first question we might be able to solve is a question on reactivity, right? If you're given some carbonyl species and asked about, hey, how rank by reactivity, or which one is the most reactive, we want to look for carbonyls with EWGs, right? So for example, let's say I have a halide that's probably going to be the most reactive of the derivative species, right? Or like some group that can withdraw by resonance. So what's a group that could possibly steal electrons from an oxygen? That's a hard question, not gonna lie. There are very few groups that can do that, but you can imagine if there was some kind of resonance group that could do that, like maybe an NO2, an acyl NO2. I've never seen that before, but you can imagine that would be the type of group, right? Incredibly electrophilic. This carbonyl would be insanely, we call hot, insanely, insanely hot. Okay, cool. But again, carbonyls, aldehydes, and ketones are what we're mainly looking for. Actually, formaldehyde would fit right in the middle here. Okay, but aldehydes more reactive than ketones. So anything we describe on a ketone, for the most part, should also work on an aldehyde, right? Because aldehydes are just inherently more reactive. And so if we look at this reaction, again, we have a reaction with an alcohol. And so oxygen-based nucleophiles, always a great place to start, right? To look at what kind of reactivity we see at the carbonyl. So just take your ketone and drop it in some water, right? And let's see what happens, right? Generally speaking, we get what we call a geminal hydrate. So we call this a gemdiol. Okay, geminal because they're on the same carbon. Think Gemini if you're like a astrology person, and diol because there's two alcohols. Okay? So we can hydrate a carbonyl, or that's another name for a geminal hydrate. Okay, cool. Now these hydrates are not very stable. In fact, they lose really quickly. They really easily lose water. Turns out that the pi bond is slightly more stable. So this C double bond O is slightly more stable than two C single bond O's. Okay, so generally speaking, hydrations are not very isoluble, but they do make great intermediates in reactions. Yeah. Like for example, the Jones oxidation is actually facilitated by the hydrate. Remember, oxidations oxidize this hydrogen only when there's an alcohol. So when we get let's say like chromium here, right? It's the hydrate that's reacting to make the carboxylic acid. Okay. So gemdiols are very good at intermediates, but not very isoluble generally. Although there are some that are isoluble, and again, it's a function of how electrophilic the carbonyl is that will tip the balance. So for example, a CF3, so a trifluoromethyl carbonyl of some kind will have a very, very, very high concentration of the diol when water is present. Okay. Actually, interestingly enough, this carbonyl here will be very hydrated, right? And so this is actually not really a function of, electrophilicity. It's more a function of bond angle, right? You can imagine this guy here constrained at 120, or wants to be 120, but actually only gets like about whatever math would be on that, I'm not sure. But this guy has a very large angle constraint, lessens it when it gets hydrated. Yeah. And yeah, generally, again, anything electrophilic or like in this really weird case where you want to have the bond angle strain release, hydration can be appreciable. But generally, again, we're not going to expect this to be a question or like an answer to some predictive products. It's just, if we throw it in water, what happens? Right? What do we observe? And we observe a hydration across the carbonyl, generally not preferable, but can be. Okay. Now, obviously, just to say this, ketones generally are not very favorably hydrated. But if we have CF3, right, which again, that withdrawing group, highly, highly, highly hydrated. So look at how much that changes it, right? It's really important to not think of this as, memorizing as aldehydes are better than ketones or aldehydes are more reactive than ketones. It's really important to understand why, right? Ketones have donating effects in them, right? There's donating effects going on. Whereas halides, halides have withdrawing effects, right? Or CF3s, right, have withdrawing effects. Completely flips the reactivity, right? Reverses it completely. So keep that in mind. I guess the cool thought to have is, well, if these are donating by sigma interactions, is there any group that can donate by resonance interaction? Right, so like an OR group, and that does exist. It's what we call an ester, which we're going to talk about later on, how to make these guys. But esters, oxygens donate in, and they increase stability. So if I wanted to draw a true stability sort of chart here, right, esters generally more stable than ketones, which are more stable than aldehydes, which are more stable than formaldehydes, right? Which, well, this is where things get a little difficult because I'm going to make an absolute statement here that may or may not. Well, I guess actually no, never mind. I take that back. If it's CF3, it's fine. But if I have like a CF3 here, yes, this is more reactive. Yeah, CF3 is definitely more reactive than an aldehyde. Yeah, definitely highly, highly reactive. Okay, cool. All right, so water, we want to add it on, diol, things that can control it, electrophilicity, or in this really weird case, right, that you should know because it's in your notes, I believe, right, bond angle strain release. Cool. All right. So what happens when we add alcohol? Something really cool happens. Okay. So let's say that I add an alcohol, an ROH, or we'll do CH3OH, so methanol. Okay? And let's say that I added an acid. Okay. And we got our first mechanism here. Carbonyls, if they're an acid, will go ahead and get protonated. Okay. Remember, alcohols, right, water, very weak nucleophiles. So you really need to motivate these guys to attack, right? If they don't have some strong motivator, like for example, an SN1 carbocation, right, they're not really going to do anything. The acid serves to, exacerbate the cationic effect on the carbonyl carbon. And so protonation is very important, must occur, because when it does, turn this positive here into a mega positive. And that mega positive can go ahead and get attacked by the methanol, okay, to form this structure here where we are half alcohol, and after this deprotonation, we are half ether. Okay. So this here, this half alcohol, half ether molecule is what we call a hemiacetal. And we can use acid and alcohol to catalyze the formation of this. Okay? You can also do this in base. So let's say that I have CH3O minus. Okay? Bases are the opposite of acid, where acid activates the carbonyl to force the alcohol molecules attack. Base is already activated, right? It's already a minus charge. So all it needs to do as an activated species is go ahead and attack. Okay, so what we get is going to be this here. It's just we'll go ahead and protonate by something, probably by the OCH3. Okay, and again, we form the hemiacetal. Okay, so hemi means half, acetal is going to be a fuller structure at the end of one of these mechanisms. Okay? But half alcohol, half ethers. So what's the stability of these guys? Generally speaking, just like with geminal diols, right? Hemiacetals, not that stable, right? I mean, it's really not that much different from the gem diol. They're both O molecules that are sharing on the same carbon. So generally, these hemiacetals not very stable, not very isoluble. So wouldn't really make sense to stop on either of these as the answer in either medium. Okay. But there is one hemiacetal that is very stable and should always be in your mind whenever you think of the formation, the possible formation of this, and that is the cyclic hemiacetal. So if I look at this particular example here, especially, right, if I have a carbonyl with an alcohol tail, this is actually a very misleading molecule, right? We draw it out as two different components, but in fact, really, it's going to be combined. In fact, 1, 2, 3, 4, 5, 6, right? This will, majority of the time, be in a 6-membered ring with oxygen in that ring, where 1, 2, 3, 4, 5, 6, right? Oxygen is 1, and attack 2. So 2 will have an O minus and a methyl, right? I'll have this methyl here. And if 3, 4, 5, 6 have anything, you can add them in, right? But in this case, they don't. But generally speaking, and then we'll have a proton transfer. But generally speaking, cyclic hemiacetals, right? These guys are stable, right? And you can play whatever effect you want on it, right? The typical culprit is, we say, entropy, right? But generally, cyclic hemiacetals, very stable. And whenever you see the possibility of forming one in your brain, you should have already formed it, right? Or if you see it, a structure like this, you should know that's a lie. The structure is not real. In fact, really what's going on is we have this cyclic structure here, okay? The cyclic hemiacetal. Okay. So cyclic hemiacetals can definitely be a final answer to something, like for example, in base. So in base, let's say like we had something like this, right? This is definitely an isolated molecule. But you can have that as an answer. Okay, so I'll put here unisolable. Okay, generally unisolable, not what we're going to see. Okay, but if it's cyclic, by all means, it can form. Okay, cool. So cool, cyclic hemiacetals can form, and if we see them, we should know they exist, and we could potentially answer them as questions. But what do we do for the non-cyclics? Do they just not proceed at all? Do we just leave them blank? The answer is no, right? But it makes sense. Otherwise, everything I just said the last 20 minutes would have been absolutely waste time, right? So what is it that these acyclic hemiacetals do that's useful to us? Well, in acid, you can imagine, well, one thing you can imagine is that this guy gets protonated again, right? And so you can see these reversibility arrows. This will go backwards, go backwards, go backwards. Not very useful to us. So let's go ahead and protonate our alcohol. Well, by doing that, what we get out is OH2 plus, a water molecule. And as they say in Davis, right, all the time, if you can make water, it will leave. I want you guys to write this down. This is your mantra for the rest of 118, okay, especially in 118C. for the most part, if you can make water, it will leave. Not even for the most part. Almost every single time you can make water, it will leave. Okay. So if there's anything that I want you guys to remember from 118B into 118C, if you can make water, it will leave. Okay. Turn water into a leaving group. Water will go ahead and leave. Actually, we'll do it here on this side. And as a result, what we'll get is this species here. Okay. Now this species, why is it stable? Because oxygen's lone pair can stabilize it, right? Can resonate with it. You guys should definitely draw out the resonance form. I just don't have the space, so I will not be doing so. But here we have a oxonium ion. Okay, this oxonium cation that forms as a result of water leaving. Right, that's how you can show this in one, without having to draw the resonance form. Now, this guy here should look very familiar, especially if I flip him over. Okay, can you guys see what this guy here is similar to? Right, maybe we see it somewhere earlier, maybe right above. Right, I think that this oxygen with a positive charge in this methyl is very similar to this protonated carbonyl, right? In the same way that the protonated carbonyl we said was incredibly mega electrophilic, right? We should think the same thing for this guy here. Incredibly electrophilic, incredibly. And so you can imagine what we saw before with the methanol tagging just happens again. And so what we get after a proton transfer is going to be this structure here where we have two acetals. If one acetal was heavy, then two, right? So hemi is half, then two should be the full. This is the acetal. Okay, our diether compound. Which, if you look transformatively, is just taking two molecules of alcohol, right, and adding them in place of the carbonyl. Okay, so our first carbonyl addition is the alcohol addition in acid to form the acetal. Okay, so acid, alcohol, acetal. Okay, our triple A. Forgot how that logo looks, but whatever. You guys get the point. Okay. So if we're in acid, you should totally expect that alcohol will drive, especially an excess of alcohol in acid will drive the product towards an acetal. And that's what you want to be, thinking about and drawing for these predicted products questions. Okay. So when I look at H, I notice again, I see the intramolecular ketone alcohol in my brain, instantly drawing this or thinking this, or maybe even just drawing my paper. And I'm thinking, okay, this is a hemiacetal. That's an acid. So if it's an acid, right, it should push forward to the acetal, where instead of having an OH, what we have is an OR group. In this case, the OR group is just going to be the alcohol we have in solution. This is going to be OCH3. Okay, and that's our first problem solved. Okay, first problem solved right there. Cool. So in acid, we're going to make acetals, especially in the presence of alcohols. Well, really, and only in the presence of alcohols. Okay. So what does that mean for base then? What happens in base? Well, if you think about it, there's no proton in solution that is labile enough for this alcohol to grab it, right? I know a lot of you can think, oh, well, O minus deprotonated this guy. And yeah, that's because this was O minus. This is OH, significantly weaker base, which needs a significantly stronger acid to protonate it. There is nothing to protonate this, and therefore we do not see a reaction, okay? At least not towards the acetal. Okay, so no acetal. That's totally fine though, because there is a use for this that we see in chapter 18, right? Usually this reaction is used to form enolates, right? Or base forms, nucleophilic forms of the carbonyl. But generally speaking, when we are in base, we do not want to think about hemiacetal or acetal formation. We want to think more about enolate formation. Okay, so you think RO minus, right? That's what you want to think about. Okay. Now, if we do have an example like this, where we have CH3O minus, right, and CH3O, where the OH and the carbonyl are on the same molecule, yes, you can think of a cyclic hemiacetal. I guess that's fine. But again, equilibrium already puts these two things together. Base would, I guess, just catalyze to be faster. It's not very useful. Oops, sorry, I forgot this. It's not very useful. Okay, so if we see base like RO minus with carbonyls, it will, for the most part, be for these enolate reactions in chapter 18, and not really for any kind of addition reaction. Okay, cool. All right. Now, one implication of this, that the fact that bases cannot form acetals, is that essentially means that bases don't interact with acetals, right? Like, I know this means it's an equal, but what I'm trying to say is that they don't interact with them. They don't mess around with them. So this leads to the idea of protecting groups, which we'll talk about when we get to the synthesis. But acetals are great protecting groups against bases if you don't want a base to react with a carbonyl. Okay, so usually the most common cited example of this is, let's say you wanted to take this dicarbonyl compound, right? And you wanted to, I don't know, add an alkyne to the ketone, right? But you wanted to keep the aldehyde intact. Well, if I just throw in alkyne, the alkyne is most definitely going to attack at the aldehyde first, right? Which is very bad. That's not what we want. So what you can do is you can protect the aldehyde, right? Turn it into an acetal of some type, right? Usually the cyclic version, and then do your reaction with the alkyne, right? So it attacks the ketone and then get rid of the protecting group. Okay. So how do we get rid of acetals then, right? When we later on talk about protecting groups and stuff, it's very simple, right? This reaction is reversible. Pushing it forward requires alcohol because that's what you're replacing the carbonyl with. So what did the carbonyl fall off as, right? What type of molecule do we form on that carbonyl O to get rid of it? We turn it into water, right? We lost water. So to push this backwards, you do a hydrolysis, you do a water reaction. So if I have, for example, this here, right? Well, first off, let's do this, right? If I have this carbonyl here and I react it with, let's say, isopropyl alcohol NH+, right? Again, to very quickly solve this, simply replace the carbonyl with two of the alcohols. It's pretty easy, right? Not too bad, right? If I want to reverse this, right, that acetal carbon, the carbon that's bound by two ethers, right, I just have to get rid of the alcohols on it, or the ethers on it, and just replace it with the carbonyl, okay? And again, how do I show this on paper? Just a hydrolysis, right? Throw in heat if you want to. Okay, so hydrolyzing carbonyls or acetals will give you carbonyls. We will see this again with amines and enamines, the nitrogen analogs of these guys. If you want to get rid of them, right, an amine or an enamine like an F, guess what? You just do a hydrolysis. Okay. Cool. All right. Now, the last thing we'll go over for acetals before we move on, just for time's sake, is just viewing the reaction from the other point. So the way that we might view this reaction currently and have our mind set on is a carbonyl reacts with an alcohol twice, right, to make OR where that carbonyl used to be, right? So that might be what we think. So again, just to kind of, sorry, I've been kind of doing this in my head and kind of hoping you guys can see this, but if I have a carbonyl, get rid of that carbonyl and just put OR. Okay. So one way to view it is you're adding alcohol, right, to a carbonyl to protect it, right, or to turn to an acetal. Another way to view this, though, is that you're taking, for example, a molecule with a diol component to it, and you're adding a carbonyl to it, right? Because it's the same thing. We're just flipping the perspective, right? Now my molecule has the alcohol portion satisfied. Let's just add the carbonyl, right? In this case, just protecting the two alcohols by giving it a carbon to join it together, and whatever the R groups are, right, we just add them in right there. Okay, so quite often people will just remember one side of the equation and run with that forever. Keep in mind the other side too, right? Alcohols, we can also do this from the point of an alcohol reacting with a carbonyl and acid, right? In that case, right, just having the diol. So usually very good questions in this involve some kind of multi-ol, polyol system where you have to kind of decide between which two alcohols can react. So whether the 1, 2, 3, 4, the 1, 2, or the 1, 2, 3, 4, right, the 1, 4 can react. And so if I kind of, sketch out what these guys would look like. So this acetal would be like a 5-membered ring, right? 1, 2, 3, 4, 5. That's not bad. Let's say I'm in acetal here. That'd be what? 1, 2, 3, 4, 5, 6, 7. 7's a little worse, right? That's very less likely to occur. And then obviously 1, 2, 3, 4, 5, 6, 7. And if they had a carbon that joined them together, 8, that's even worse. Okay. So if I were to take, let's say, an acetaldehyde, again, anything we just try with the ketone also works with the aldehyde. That would give us the protection of, or the acetylation of these two alcohols here with that acetaldehyde, right? This is the acetaldehyde methyl, and then the acetaldehyde aldehyde proton. Yeah, cool. All right, so that's the whole thing on acetal, so we'll just call it there for now. Okay, let's move on to amines and enamines. So F, right? Now again, if you notice, there actually isn't an amine question anywhere on this or an enamine question on this, which I guess I could have done a better job of, but it's okay because the tricks to this is pretty simple, and it follows a lot of how alcohols work. Okay, but anyways, so let's say we have a ketone, and we react the ketone with a primary amine in acid, right? Again, kind of the same ideas, right? We can go ahead and protonate. It's all reversible again. And so we can go ahead and do that attack there. Now that I think about this, I actually want to write this in a different way. I know that they teach you guys this mechanism differently, but it's good to know the correct way to do this. So in fact, actually, if you think about this, between oxygen and nitrogen, actually nitrogen's the better base. So in fact, always nitrogen should be what protonates first. Okay. And then it's the nitrogen that can protonate the carbonyl afterwards. Okay. So I know this seems like an extra step, but it really is vital to understand this. And in my opinion, more correct, right? Amines are better bases than oxygen. So mechanistically, amines should protonate first. This will help you out in 118C, by the way, to know this. Okay. But anyways, once it protonates, eventually over time, right, the amine can protonate the carbonyl. And as it protonates the carbonyl, right, that lone pair that the amine just came back, it donates right back into the carbonyl. So nothing is lost. So what we get is going to be this here. For the most part, the same thing, right? Where we form a hemi structure. In this case, I'm just going to kind of get rid of the proton here, but yeah, I didn't want it to do all that, but it's okay. A lot of proton transfer, right? We'll get here to the hemiaminal. Okay, cool. Now, once again, we can add a proton, make water. And the amine can use its lone pair to help kick off that water. And what we get out is this species here. Okay, cool. Which we call the iminium ion. All right. Now, with alcohols, right, if an alcohol gets to the point with a carbonyl where it forms the protonated version here, right, we said that the alcohol just goes ahead and attacks, right, because that's what alcohols do. They just act as nucleophiles to these centers. Okay? So it's very safe to go ahead and think that the amine does the same thing, right? The amine goes ahead and attacks here, right? But remember, amines, not only are they good nucleophiles, they're good bases. And as we saw in the beginning, right, this is such a significant effect, its basicity, that in fact, the first thing that happens in the mechanism is the amine acts as the base, and then it protonates the carbonyl. So if an amine has a choice, whether it can act as an acid or a base, sorry, as a nucleophile or a base, turns out the amine is going to act as a base instead. And so instead of attacking at that center to form an aminal, for example, what we get instead is the formation of an NC double bond, an imine. Okay? And this is what sets apart alcohol reactions from amines, right? They're not just the same. It's not like we can just say, oh, everything you learned about alcohol you can apply to an amine. It's not the same at all. Okay? Cool. Now, looking at this visually, it's pretty simple to see how this forms out, right? You're literally just taking, right? If we kind of look through here, we just kind of replace the nitrogen with the oxygen. So you can just redraw your carbon compound, get rid of N, and just put R in its place. Pretty simple. Okay. But one thing to notice here is that we lost 2 hydrogens in the process, right? So 2 hydrogens are required to form an imine. So what happens when I have a secondary amine? So if I get to the part in the mechanism where I have an amine such like this, right? So I use a secondary amine instead, right? Let's actually write it this way. Right, so I have this mild acid. Okay, we get to this point here, right? What's going on? What's going to happen? Does it finally happen where we override the whole, oh, bases, amines are bases, and because they can't attack here, that's not a proton. They can't attack here, that's not a proton. So maybe they just attack here. Well, secondary amines are still pretty bulky. So, nucleophilic attack is still pretty hard here. We're still going to act as a base, but at a different center. Okay. And that's going to be at the carbon that is right next door to that carbonyl compound or that iminium compound. The amine connects base, which kind of funnels electrons inside to form this species here, an alkene and an amine. Or, yeah, I guess an amine. So this is an enamine. Okay. So primary amines form amines because they lose 2 hydrogens to form the amine. Secondary amines, which only have 1 proton, go through the enamine where carbon donates that second proton. Okay, and we form this double bond right over here. Okay. Now, enamines kind of bring up this sort of regiochemical nightmare where if I have a carbonyl like this one, right, how do I know? Right, how do I know which side to form the double bond? For this class, it's okay to think in terms of double bond stability. So if I have the pi bond here versus here, the more stable position is that inside position, right? That more sub position. So it's okay to do that in this class, although technically you might read online that's not correct. It's okay. We're just lying to you guys anyways all the time. So it's okay to think that it's just okay. Okay, cool. So if you think about it, if I try to do a reaction with ammonia, right? Ammonia has 3 protons, which is more than 2. So we know that's just going to be replacing the oxygen with nitrogen and H. Okay, pretty simple. Okay. All right. Now, again, we can also do intermolecular variants. That's totally fine. Just keep in mind what this is here, whether it's NH2 or NH, and just form your cycle. So if one attacks here, this is 2, 3, 4, 5, and 6. So N is going to be the ring with 6, right? 1, 2, 3, 4, 5, and 6. I'm only going to write 1 and 2 because the rest of the numbers don't really matter. At 2 is where we're going to have the OH. We'll have the H here. Again, we'll lose the OH as water, right? But it doesn't really matter, right? Because since 2 is the carbonyl carbon, we know that enamine is going to form the double bond just going to form right there. Okay, just like that. Ace will form this imine here. If I had, let's say, a molecule like this one, right? Same idea, but this time, right, instead of forming the imine, right, I'll form the enamine. So we'll form that there. Okay. Again, let's say this were a ketone, right? That were a ketone. Then again, future person is this side, and this side for the pi bond, definitely going to be the left side, much more so. Okay. So amines, enamines, not too terribly difficult. Just again, keep in mind the idea that amines are better bases, right? So that's why we form these, these different compounds. Now, F, again, F is already an enamine, right? So we don't have to really learn too much there. It's the hydrolysis that we're trying to figure out, right? When we hydrolyze these, what's going to happen? And so again, every single, acetal, amine, enamine that you hydrolyze, it will always return you back to the original carbonyl. How do you predict those with absolute accuracy? No doubt about it, shadow in your mind. It's very simple, right? We kind of went over the trick with acetal. Acetal is super simple. You just look for that acetal carbon, the carbon bound by two ethers, and you kind of just get rid of them and you just replace it with an carbonyl. So hydration complete. For an amine, it is terribly easy, right? You just replace the N with an L. No questions asked. Enamine is a little more difficult because you have to think about it for a second, but it's not too bad, right? Because we can use a bond to help us here, okay? But you can use the heteroatom bond to help you, but to know which NC bond to cut, because let's say that we have a tertiary amine where everything's drawn out, and you're like, which NC bond do I cut off and replace the carbonyl? Let the pi bond guide you, because the pi bond's telling you where that carbonyl used to be. So I know that out of 1, 2, and 3, we're going to cut at 3 right there, right? And right where that NC bond used to be, we can form that carbonyl. And that's a hydrolysis. So in this question, right, we have these 3 carbons that are bound to nitrogen. Which one has the pi bond? That's on the left here. So I know that right, that's going to be my carbonyl compound there. Or there. That should be it. Cool. Right, where this is an aldehyde. Cool. All right. So that's our enamine and enamine collection. Now, with that being, now that that's said out loud, you guys should really practice your mechanisms for backwards reactions as well, especially the acetal amine enamine mechanism. Very, very popular question on the final to ask you not to go forward, but to go backwards. And so many people complain that it's like the hardest thing or the most unfair thing, but it actually isn't very unfair. Once you realize, again, that these reactions are reversible, okay, there's a very specific type of reversibility at play here. We call this microscopic reversibility, okay? What is that jargon for? That's just very high-level jargon for, the intermediates going forward in a reaction are the same as those going backwards. So if you feel comfortable forming an amine, then you're actually comfortable breaking an amine, because guess what? It's literally this process here. So by all means, please practice this, have this down, right? If you can go one way, guess what? It's a buy one get one free opportunity, because you know how to go backwards. It's the exact same intermediates, just in the backwards process. So I could almost even just formulate a mechanism just from these forward arrows of the backwards reaction, right? As long as I know these intermediates here. Okay, so how would this work, right? Well, hey, let's use the intermediates to guide us if we're not sure of the arrows. So from here to here, right, I go from imine to iminium. So clearly this is protonating. That's cool. Okay. From here to here, I'm going from iminium to hemiaminal, so hydrated imine. So I'm just going to go ahead and add water. Right, easy. From here to here, water gets deprotonated. From here to here, right, we lose. Oh, actually, there should be a protonation here, but we'll deprotonate the water. We'll protonate the amine. From here to here, we see we lose the amine, so we're going to go ahead and kick it off, right, to form that carbonyl cation, and then we get a deprotonation, right, and there we have it. So please practice these backwards, or at least be comfortable with one way, because if you don't do it one way, you know the other way. Okay, don't doubt yourself. Okay, cool. All right. So that's all I'm going to spend time on the amine and enamine section for this. Cool. All right. Let me see, actually, are there any on this one? Amines or enamines? Oh, I just realized there's one other one we can talk about. So nitrogen, oxygen, sulfur, right? NOS, we can see how they kind of line up. If you had to guess how sulfur reacted in terms of if it's closer to oxygen type reaction with carbonyls or nitrogen, right? If you had to guess real quick, I'd guess oxygen, right? And that'd be correct. So if you ever see a sulfur molecule, just treat it like an oxygen in terms of how it reacts with carbonyls. In this case, we know that we're going to turn this into, like an hemiacetal, sorry, an acetal with like sulfurs, which we call a thioacetal. Okay. Now, thioacetals kind of have two fates to them, which makes them kind of interesting. So we can form this from this, this. Okay. To break this down, mercuric chloride in water, right? Don't worry about getting all the parts of the reaction soup. If you really are paranoid, know all of them. These are the most important ones. So mercuric chloride to help break down the acetal, and the water to, eventually replace it in hydration. Okay. The other phase is H2, rainy, or H2PD, essentially H2 and metal, okay, that will hydrogenate or get rid of that sulfur completely. It will deoxygenate it. Okay, which is really interesting because that means that H2 now has a new application in this class. Alongside, being able to interact with alkenes, it can now interact with the sulfur molecules. So keep this in mind. This could be a great sort of tandem reaction, or consequential reaction, right? I guess I should have wrote that actually. I wasn't thinking when I wrote this. I should have wrote that. It's my bad. Cool. All right, so sulfurs react just like so. Just one last thing, right? Like if I had CH3SH and zinc Cl2, should not be surprised. This will give me SCH3, SCH3, or if I had like a sulfur arm right down here, right, I shouldn't be surprised that this will probably be cyclized, right? And then if I added more sulfur, right, then it would be like a thioacetal cycle, something like that. Right? Should not surprise you guys. They're in the same column. Okay, cool. All right. Those are our major addition reactions. Okay. The rest are kind of interesting reactions or thought experiments. For example, if N and O can add on to the carbonyl, is there any way to add C on? And there is, right? We can do a Grignard reaction. So we've already learned this, right? We can do the Grignard reaction, which is a pretty cool reaction. But what if I wanted to do the reaction of an imine, but with a carbon? So instead of replacing, instead of getting rid of the pi bond, right? What if I just wanted to replace the O with R, right? Potentially R. We can do that, right? That is the Wittig reaction. So E over here is going to be our Wittig reaction. So how does Wittig work? Well, Wittig can begin with some alkyl halide, and the reaction of triphenylphosphine in the alkyl halide. Also, phosphorus, if you remember from 118A, pretty good nucleophile, right? It's large, on the basic side of things, can do a very good displacement here. And what we get out is this here, triphenylphosphonium, highly electrophilic compound, or at least it makes this carbon very electrophilic. Okay? That if I have some kind of base, usually N-butene, right, which looks like this. So we'll just put this here. It can pull off this proton, form an anion next to this cation. Okay. And this here is what we call a phosphonium or a phosphorus ylide. Okay, so what is an ylide? An ylide is a carb anion next to some heteroatom cation. So if I have a carb anion and some heteroatom A with a cation, this is an ylide. And the ylide is usually named after whatever the identity of A is. So if it were a sulfur, right, we would call this a sulfonium ylide. Phosphorus is phosphonium ylide. If it were a nitrogen, we call this a nitrogen ylide. Actually, I don't know what you would call the nitrogen ones, actually. I know they're called ylides for sure, but I don't know what you would call the end part of this. I don't actually know. Something I should look into, I guess. But you would call this a nitrogen-based ylide. Okay. Anyways, phosphorus ylide. Most important part is you notice that the carbon is nucleophilic here. So we have a way of making a carbon nucleophile reagent, which is in resonance with the phosphonium to form this compound here. Okay. Now, don't let that double bond fool you. Again, it may look like it's being shared equally, but we can see here that the anion is cleared of carbon. So that when we have a carbonyl compound within vicinity, okay, and I'll use an aldehyde in this case, right? When that pi bond attacks, we are very clearly attacking from carbon. So it's very clearly the attack is from carbon, to be honest. Okay. Now, if I kind of draw this out, right, carbon, that carbon there that attacked, which I'll kind of mark with the star that attacked, right? We have a phosphorus. It's going to be positive, right? And we'll have this H for aldehyde, right? This is going to be the result of the Wittig reaction or the Wittig reagent, the alide adding on. Okay. Now, here's a very cool thing about phosphorus. Phosphorus is in love with oxygen. Okay. I mean, if you look at the periodic table, right, phosphorus is always has been kind of staring at oxygen from afar, trying to wonder exactly who they are, what kind of vibe they have, right? You want to ask them out on a date. Phosphorus is in love with oxygen. So sulfur is kind of like the big older sibling that's like, hey, back off, right? Like, get out of here, weirdo. But anyways, whenever phosphorus has a chance, it will always snatch oxygen, or it will always try to form a bond with oxygen. And guess what? We have an O- species with a P positive. It's almost like they were made for each other. They have the right chemistry. So what ends up happening instantly is oxygen bonds with the phosphonium, or the phosphorus, to form this really funny and cheeky shape here. Okay, this square. And so I know we've always told you guys squares are bad. Turns out phosphorus love for oxygen is strong enough to overcome the badness of a square. And so this square has a name, we call it a betaine. Okay. But this betaine undergoes a very specific reaction. And phosphorus wants to elope with oxygen. Oxygen still hasn't said a word yet, but phosphorus is doing all the work here. Phosphorus and oxygen are going to leap together, right? We're going to break their bonds to the other side of the molecule. We're going to form a double bond between them. Oxygen is going to give up its bond like that. To be honest, it doesn't really matter how you do it. Whether you do it like this or that way. The point is you want to be breaking off P and O from this molecule here. And out you get is going to be, oh, I'm missing a carbon. Sorry. This one, I was like, why in the world is this not making sense? There's supposed to be something there. It's because I forgot that carbon there. I apologize. Oh, I see. I drew the H there like that was the aldehyde carbon. That's why. My bad. Okay, anyways. Cool. All right. But anyways, we're going to go ahead and lose that there. And what we get out is going to be an alkene and this triphenyl phosphine oxide compound here. Okay. Again, PO make very strong bonds with each other. So generally speaking, if you ever want to dehydrate oxygen very easily, actually, you don't really use H2SO4, you use phosphorus. So all those dehydration reactions you guys learned before, generally speaking, these are actually industrially done with POCl3. Because phosphorus just makes such amazing bonds with oxygen, pulls it off really, really easily. But I digress, right? I'm trying to, whatever, I'm digressing. But anyways, with this, we can successfully pull off oxygen and insert a carbon bond, right, to form an alkene. Okay, and so this is how we replace the carbonyl oxygen with carbon. Now, what you'll notice is I specifically wrote here the cis isomer. Generally, the cis isomer is the major isomer when it comes to alkenes that are formed. So, for example, let's do the reaction here like this with this phosphorus elide here. Okay. Again, we're essentially going to be transplanting these three carbons in place of the oxygen. So 1, 2, 3. We will get this oxygen here. We want to add 1, 2, and 3. Like that, 1, 2, and 3. One thing I always tell people is it's very easy to mess this up because you want to do this 1, 2, and 3, right? Because you're adding 3 carbons. But remember that this itself is becoming a carbon. So in fact, it's 1, 2, and 3. Very, very common mistake. Just keep in mind, always I advise is it should feel like you're doing it wrong or that you're 1 short, and then you've done the Wittig correctly. Okay? But we form the cis isomer. Okay? Because this Wittig reagent here is a very normal reagent. Nothing's too crazy about it. The only time Wittigs form the trans isomer is if that Wittig is conjugated to like a carbonyl, okay, or some kind of EWG. And so conjugated means that the pi bonds are next to each other. So in this case, if this were the case, right, again, 1, 2, and 3, draw this here. Sorry. But if I draw this here, right, I'll have this, and replacing that with that there. So 1, 2, and 3. 1, 2, and 3, where 2 has the carbonyl, right? Now we have the trans isomer, or the, I guess in this case, the E isomer. This would be the Z isomer. Okay. What's the reason for the selectivity? It's a bit of approach chemistry. It's how these two reagents kind of approach each other. It's not something worth worrying about, but if you really care, if you want to know more organic, learn more organic, then go on the internet, you'll find the answer for this. Okay. But Wittig reaction, pretty cool, right? Allows us to kind of replace these oxygens. Also allows us to make alkenes much more reliably, right? If you think back to 118A and even the beginning of 118B, really the only way to make alkenes was via E2. And E2 kind of was a little tricky, right? For the most part, if I wanted to make an alkene, it would either be trans or, depending on the antiperinarity of a proton, it could be E or Z, right? So whether this is E or Z will just depend on the H and the Br, right, where they were in space. But if it's trans, it's usually mostly just trans. Making cis alkenes was almost impossible. And if you ever drew on an exam last quarter, kind of all this laughed at you guys, right? Well, guess what? Now you have a way to make trans alkenes very, very easily, right? On top, sorry, cis alkenes very, very easily. So I meant to say, I apologize. If you ever drew a cis alkene, kind of laughed at you, but now you have a way to make them, right? On top of also knowing how to make them from alkynes, although alkynes were a little tricky, right? Because alkynes were, you would need to do H2, right? But you don't have access to the disub, right? So anyways, or you have to do, sorry, it was H2, not what I'm doing. It's late, I apologize. Yeah, H2, we learned catalyst, so earlier in the quarter we learned this. Anyways, point being is that you guys now have a lot of access to this material. We have a lot of ways to make alkenes now. So if you ever suspect the formation of an alkene, instead of doing alcohol dehydrations, consider a Wittig, right? Wittig is a very powerful tool. Okay, cool. Now again, this reaction works okay with ketones. It's not bad. Really where these guys shine are on aldehydes. So aldehydes are a lot more electrophilic, a lot more steric too. Okay, so if you were to react this with, like, let's say this, and you're just replacing that oxygen, make a cis isomer, 1, 2, 3, 4, 1, 2, 3, 4. Okay, and there you go. Okay, cool. You can do intermolecular Wittigs too. It's not like the craziest reaction, but it would just have to be set up really weird. Like you'd have to start from here, and then you'd have to be here, I guess. I don't know. This, I mean, as we'll learn, this is not the most reliable reaction because actually both of these all 3 of these protons are actually kind of very closely electrophilic to each other. So it's not the greatest reaction ever, but I guess there's a possibility for intermolecular Wittig. Cool. All right. We'll call it there on the Wittig. But when we look at this molecule here, right, it's like we're doing 1, 2 across this. So okay, we want to make the cis isomer, the Z isomer, so 1, 2, and then step 2 is MCPBA, so we're just epoxidating across that. Okay. Cool. Now this is racemic, by the way. I know I didn't really write it, but you guys should never forget this. That things can be racemic. Cool. All right. So up next on the docket, outside of Wittig's, it's going to be the deoxygenations. That is just, we kind of already talked about one. There's actually a name for this, the sulfur variant, where you go through this and you kind of get rid of the oxygen. The name for that is the Mozingo. Right, so this would just be this Lewis acid and then H2 and rainy. Right, that's just Lewis acid. You can also do this. So this would be considered like a neutral condition, right? Because it's a neutral reagent to deoxygenate. You can also do this. I mean, we saw this earlier in the quarter, right? With benzoic ketones. Do this with Clemenson. This is highly acidic condition, but you can do it. Okay. So if we have a neutral and an acidic version, there must be a basic version, and there is. And that version is known as the Wolff-Kishner reaction. Now, I know I'm showing this on an aromatic, but it's not required that this is aromatic. Right? I'm just showing it on here so you can do it here as well, sort of the basic version. Okay? This reaction, you do need to know the mechanism too, and it's a very great contender for the final, so please practice it. But how does this reaction work? Well, we kind of learned the first part, right? If I have an amine compound, right? An amine compound, especially if it's primary, it doesn't matter if there's two nitrogens, honestly. You can have two nitrogens, that's fine. But we know that primary amine replaces oxygen and in its R group to form an imine, right? And so we form this hydrazine here, okay? Or hydrazone, I guess, or I guess you can call it, yeah, hydrazone compound here. And you can practice the mechanism on this if you'd like. I know on one of these exams, I have this as a mechanism question. So the key does go over how to form this if you had to, but you can totally do it. Go from here to here, tiny minute from the practice. Okay. But from here, right, what happens to facilitate sort of the removal of the whole group to form to form a CH2 there? Well, first off, if I look very carefully at the system, I have an NN single bond next to a pi bond, right? If I were to replace those with carbons, right, and highlight this H here, what would we call that H? It has an A name. It's an allylic hydrogen. And allylic hydrogens are mega acidic, right? Incredibly acidic, right? Or, okay, not incredibly, but generally speaking, we learned that they are very reactive positions. And so if I take two carbons, replace them with nitrogen, guess what? This becomes incredibly, incredibly acidic, right? Very, very willing to lose a proton. And so even a base like hydroxide can pull off this proton here, right? And sort of give us this allyl system. And so you can imagine this anion resonates. If you want to draw it, you can show it. Up to you. I'm just going to skip it just for sake of time. But this anion can go ahead and protonate right off of that water. And so congratulations, you've now successfully done your first hydrogenation towards CH2. So if all it took was deprotonating this right on the N, right, putting a hydrogen on N and then placing it on the carbon there, let's just do it again, right? Let's go ahead and deprotonate this hydrogen. Well, it turns out deprotonated this hydrogen is actually very, very easy despite not having the allyl system, because when these electrons swing down, right, they can form an N-N triple bond, and an N-N triple bond represents N2, an incredibly stable nitrogen molecule. Okay, N2, for all intents and purposes of this class, is the best leaving group in the world, and anytime you can form it, you should, so that you can proceed, you have your reaction proceed forward. So this reaction is very special because every single arrow is to some extent reversible until this step here where you lose N2. And out you get is this anion, which again, almost instantly in solution, just protonates off of that water that we just made to get out the deoxygenated center. So this deoxygenation relies on removal of the carbonyl as essentially N2, right? We're forming the N2 molecule, best gas ever to exist, forcing it to deoxygenate or, to lose oxygen overall, like formally deoxygenate. Okay, cool. And again, like every single mechanism, we can kind of boil it down to a couple of different trends, right? And mainly in this one being that, hey, we're just kind of deprotonating on N, right? And then protonating back on C, deprotonating on N, losing N2, deprotonating on C. Okay, cool. All right, so that's one. Practice that one. It's a good one to know. Okay, that was the one on my final, actually, was the Wolff-Kishner deoxygenation. And I remember seeing it like, oh, yes, I'm so happy because I practiced that one a lot. I like the transformation. I thought it was pretty cool. Cool. So anytime you see this, is there any Wolff-Kishners on here? I know there's on one of the exams, there's a Wolff-Kishner. Oh yeah, right here, right? You see that, you know that you're essentially just getting rid of this and this, right? So just like that, boom, no questions asked, right? And so this is sort of the basic complement to this reaction. So you have three different ways of getting rid of these carbonyls. Why might you choose one over the other? In a much more advanced class, one that makes you think a little more, you might sit down and consider different things like, does my molecule respond well to base? Does it respond well to acid? Do I need to protect anything of it? Blah, blah, blah. For example, let's say that I have a ketone here with an alkene, right? Would any of these deoxygenations be harmful towards the alkene? I think of one for sure, right? H2 rainy, right? That would hit the alkene, so that would be a big bad no, right? We wouldn't want that. Acid or base might be better here, although actually, let me change this because acid or base actually would be pretty bad here for a particular reason, but now this is a little more safe. Now H2 would be bad here, but acid or base might be a better choice, right? Clemenson or, I would go Wolff-Kishner here, honestly. That would be a possibility. Another, part that might kind of suck is, let's say that I have, let's say that I have like a bromide here downhill, and I have this here, right? In which condition might this suck? Well, I would probably not want to do Wolff-Kishner here because Wolff-Kishner here does have nucleophilic hydroxides that could potentially backside here, cause some issues, might go for the acid approach or the neutral approach, right? Now, in a higher advanced class, you would be asked to think about that. Fortunately for you guys, unfortunately for me, right? This is not that higher advanced class. So it's okay if you kind of use whatever you want. I just kind of say stick to one and just use it. For example, hydrazine, that's a good one to use kind of all the time. So if you feel the need to deoxygenate, that's what I would do if I were you guys. Okay. But unfortunately in this class, again, fortunate for you guys, right? Great thing for you guys is that we don't really think too hard when it comes to these, right? We don't really force ourselves to push to that level. Cool. All right. So that's the deoxygenations. All that's left now, I think, in chapter 17, outside of deoxygenations are, I think it's the Baeyer-Villiger. Is that what's left? I guess I could check. I have the book. Yeah. What is this? Yeah, so amines, deoxygenation. Oh, HCN, Wittig. Okay, yeah. So basically, yeah. Okay. Cool. We're pretty much almost done with this chapter. Let's just do this one really quickly. NaCN HCl essentially replaces the carbonyl with OH and CN, the cyanohydrin. This is a very straightforward reaction. Not much to think about here. The thing you guys need to know, though, is that cyanohydrin has two fates. If you do lithium aluminum hydride, that will turn this into this here, this amino alcohol. I want you guys to notice how this amino alcohol is vicinal, right? So a very good cue that you might need to do the amino alcohol reduction, or the cyanohydrin reduction, is this Q here, is that it is a vicinal OH NH2. Okay, that'll always be the relationship. Doesn't matter what is here. This could be R, right? This could be a ketone, aldehyde, doesn't matter. That doesn't change anything. Okay. The other faith is that you can do a hydrolysis on the nitrile to form a carboxylic acid. So you guys now have another way of making a carboxylic acid in this class. It's through the nitrile. So consider it possibly if you need it. You might need it for one of these syntheses, I'll tell you that. Yeah. Cool. All right. So that's the cyanohydrin reaction, all you need to know about it. Baeyer-Villiger, pretty cool reaction. Take a carbonyl compound, you MCPVA it, guess what? Turns into an ester. So how does this reaction work? Well, MCPVA, again, it's a proxy acid. So I'm just going to go ahead and put R here. That part doesn't matter. What matters here is that we have this proxy acid, which again, acids, their job is to protonate. And that's what this does to the carbonyl. We'll just add in there. And what we end up getting is this compound here. Yeah, cool. All right, so we have sort of like a NBS-style type situation here. So again, with these sort of alcohol compounds, we saw that you can proceed an acid to the acetal. Peroxy acids are a little bit interesting though, right? Last time we saw peroxide, last time we saw peroxide add to anything was in those boronate esters, right? Or those boronate species where we were trying to, right, add on R groups, right, onto those oxygens, right? Or we had this sort of push-pull mechanism. Guess what? It's pretty much the same thing. We're going to have the same type of push-pull. It just requires a little bit of extra movement here. The oxygen swings down and kicks one of its R groups, onto that O, so that we can kick off the rest of that acetate group off, and that O group off as a leaving group. Okay? So that's how we get sort of the ester formation here. Right, so we get the R group pushed over on one of those oxygens. Okay? Now, what determines which R group goes instead of the other? Something we call migratory aptitude. You'll have some list shared in class for this. It's like tertiary, secondary, which is about equal to phenyl. So like, it looks like this. Primary, and then H is a little bit up here. So because H is a little bit up here, that actually means that anytime you have an aldehyde and you do this reaction, O is always inserted on the H side. So it always forms the carboxylic acid, no questions asked. Okay. On a ketone, you will have to look left or right once it'll add in. So the more subside, that's kind of the train here, right? So more subside. The more subside is the secondary side. So left side stays the same. We had an oxygen on the right side and then 3 carbons. 1, 2, 3. Oh, wait, what am I? Oh, oh my God. I'm so weird here. It's because I saw the MCPVA. That's funny. Well, I guess we can still make that work, right? That was the case, right? That would be the answer there. I think there's a question on the other side, on the other exam. Yes, there is. There's this one here. Right, how would this work? Again, what side is going to be the one that inserts? Right side's more substitutes, we'll insert on the right. So for the most part, this stays the same, right? We just insert here, and then we have to kind of, sort of push down on 2 carbons, right? Like that. So like that. Okay. So notice how the ring expands from 6 to 7 when we do that. Okay, cool. So just keep that in mind. This is also really good for synthesis because it means that there's only one way right now to make esters in synthesis, So if we see esters, do you know where they came from? It's a really easy way to retrosynth. It's just, oh, they were just ketones. Aldehydes, which is MCP, right? So way to think about that. Cool. All right. With that, that's pretty much it. Baeyer-Villiger. Yeah. Last thing is just the oxidative tests. If you have an aldehyde and a ketone, right, and you expose them to some metal and hydroxide, ketones do not react, but aldehydes do. Aldehydes oxidize into carboxylates or carboxylic acids. Okay, so this is just the one to keep in the back of your head. This is like very, very low yield material. Cool. All right. Well, with that, I mean, that's all chapter 17. Chapter 17 material that we need to know. I know it's a lot. I mean, it took us about an hour to get through it because it's about a good chunk of material. Chapter 18 is smaller, but it has like more intensive material, I think. But before we get into that, let's just, just to kind of finish up on chapter 17, a lot of the stuff we went over was reactions, right? And theory on those reactions, which is a good thing to have and know. When we think of what can be an NR question from chapter 17, not very many things, right, can be NR. For example, I mean, I guess one thing that could be NR is, well, the last thing we just talked about, right? If I have a ketone and I try to do some sort of like response tests on it, like these oxidative tests, these metal cations in hydroxide, right? This is an NR for sure. But outside of that, I mean, what else could be an NR? Oh, just talked about this. Let's say I have an acetal and I try to react it in base. Right? Remember, base is completely inert when it comes to acetals. No interaction. This would be NR. So any kind of acetal, I drew a cyclic one, but this could be any kind, right? Absolutely no interaction is going to happen between that acetal and the base. That could be another NR type question. Same thing with this too, actually. If I try to do OH minus here, right? We didn't really talk about hydroxide in the reactions of sorry, my mic dropped. But we didn't really talk about the reactions of amines, enamines with hydroxide. So you can assume that base is not going to interact with them either, which is for the most part very true. Okay, cool. So what else can I think of for NR? Yeah, kind of drawing a bit of a blank here, but that's about it for NR. I mean, Wittig doesn't really have an NR condition. It just has conditions that kind of suck, but not really much of NR that I can think of. Right? You're just adding a carbonyl. One really cool application of the Wittig actually is this reaction here. Actually, I wanted to put this on the exam, but I deemed it might be a little too hard. But if you MCPVA this, right, to form this, and then add in triphenylphosphine, where triphenylphosphine is a very good nucleophile. So you end up getting this here, which is, again, you have an oxygen and a phosphorus next to each other. Again, phosphorus is in love with oxygen. They want to be on this, it wants to be on the same side. And when we do that, guess what? Right? We are able to form that betaine again. And so essentially, we need to kind of condense the arrows here very quickly, right? We can kind of do something like this. Right. I know those areas are a little weird, but we can kind of do something like that to kind of condense those areas very quickly. And we can make alkenes from epoxides very, very easily. In fact, actually, if you kind of think about this, this is kind of like how we isomerize transalkenes into cis ones, right? You just epoxidate them and then throw in some phosphorus, get you that cis alkene. So cool application of that reaction. But, I'm kind of drawing the blanks on NRs. If I think of any, I'll definitely mention them, write them in those extra problems. Just right now, I'm not able to see anything. Cool. All right. So I'm going to close a chapter on 17. We're going to open up on 18 into the enolates chapter. Okay. Enolates chapter. Actually, before we do that, let me just scan here. Scanning. I guess there's a couple things we could do here. One is that so we did this. That's this. We did this one. Right. That's this. Okay, and we didn't do this one, so that would just be right. We would just 1, 2, 3, add that in place of oxygen here. So 1, 2, 3, like that, and then we can do the second step once we finish talking about chapter 18. We can do E. E is just getting rid of the thioacetal, putting in a carbonyl there. And then the G, first part of G, right? Secondary amine ketone, right? We can form an enamine. So we have a carbonyl here. And then in its place, we will form carbonyl just like that. Or sorry, enamine with the pi one. Either side doesn't matter, right? If there were like a methyl here, maybe we might be more inclined to, go on the right side versus the left. Okay? But outside of that, we've kind of completed all the reactions for 17. So let's get into 18, the final chapter of the quarter, right? So excited. Chapter 18 is all concerned with the enolate. So if I take a carbonyl compound, I mentioned before, RO minus, right? Not the greatest at doing, acetal and acetal type chemistry, but it's a little bit better at pulling off these protons here. Okay? So we can go ahead and pull off the proton from, let's say, a ketone. And what we form is this resonating system here, which is what we call the enolate. Okay, so the enolate's a very interesting species, right? It's what we call an ambident anion. It's an anion on oxygen and an anion on carbon. So it's a resonating system. It's an allyl system, if you think about it, right? If I got rid of that oxygen, right, that's an allyl system. So we can see where some of that stability is coming from in this, right? So it's allyl. Okay. It's on oxygen and it's carbon. So you can imagine oxygen is doing a lot of stabilization in this resonance form. Okay. pKa for these protons for ketones is around 20. For aldehydes, this is around 18. So again, aldehydes just being a bit more acidic just because, again, they're a bit more electrophilic. So overall, a bit more cationic, a bit more acidic. Okay, those protons are easier to pull off. We'll see in the grand scheme of things, it's not totally terrible, but anyways. So we can pull off these protons and form this ambident anion. Okay, an anion that can exist on O and can exist on C. Okay, now generally speaking, for the reactions we will talk about in this class, the anion will, for the most part, react at C. Okay, that's not to say that O reactions can't happen. Oh, they can, but we're just going to ignore them just for the simplicity and just keeping our brains safe and sound while we are learning this material. Okay, but yes, they could potentially attack at O, but we'll concern ourselves with attacks at C. Okay, what can these anions attack? Well, just think about electrophiles. One particular electrophile we can think about is a halogen. So in enolates, let's say that I have here, and I have RO minus. Go ahead and attack at C, let's say like a bromine. Okay, that's totally possible. Get what we call a bromination or an alpha bromination. Right? Totally possible. You can get this here. Okay. Now in base, okay, when we add this proton here, right? Remember, base pulled off this proton in the first place. Base might be motivated to pull off this proton once again. Because I mean it's a proton, right? That is now not only inductively being pulled on by the carbonyl, but also the bromine. So this becomes more acidic. And so what we end up getting is another removable proton by this. And you can imagine another attack on bromine. Okay. And so what we end up with is a dibrominated species. Well, hey, we have a dibrominated species. Who's to say this hydrogen won't want to fall up too? And it does as well. So in a halogenation reaction in base, right, as I add more of these bromines on, right, the protons that are left at that position next to the carbonyl become much more acidic. Okay, well, I guess I should have said this. We call this the alpha position, right? The alpha position. Okay? So these protons at the alpha position get very, very acidic. So you can imagine eventually, right, this will turn into a species where all three hydrogens are sort of replaced by the bromine. Okay, so they're replaced by the bromine, just like that. I'm going to go over here real quick and just look at a different type of species here, because we'll come back to this in a second. But if I have, let's say, Br2 and NaOH, you can imagine then that every single bromine or every single hydrogen position, alpha hydrogen position, will essentially be affected and effectively replaced by a bromine. Okay. As a base, the more and more you add the bromines on, the more acidic those hydrogens become. So we get what we call a complete halogenation in base. Okay. By the way, if it wasn't, I guess that segue was kind of weird. I'm going to solely focus on reactions for 18. Any sort of conceptual stuff will come back, with the other like MC questions. There's a couple MC questions that cover like conceptual stuff. So we'll cover that when we get to it. But let's just skip through the reactions so that we can hopefully wrap up in about half hour and just kind of blaze through the rest of the midterm questions. Okay, cool. All right. Just in case that felt like a weird segue. Cool. All right. So bromination in base leads to complete halogenation. Okay? We can also do bromination in acid, right? But acid doesn't form an enolate, right? Enolate's a base form. What acid forms is the enol. So enols, essentially, let's say I have some acid here. Right? Yes, the conjugate base will just pull off that proton and will form the enol just like that. And so an enol can also do this reaction. Go ahead and attack a bromine. Out we get is the alpha bromide. Now, looking at this species, right? Again, the starting of the reaction to kind of promote the pull out the proton is this basic action, right? The basic action of attacking this proton. We just saw that adding bromines, right, adds acidity to the molecule, right? It adds acidity to the carbonyl. So the fact that adding a bromine made the alpha position much more acidic, right, kind of facilitated the basic action across it. Well, if adding these bromines makes the molecule more acidic, then acting as a base is going to be harder, right? Now, what I think about it is that these bromines can inductively pull on these electrons, making them a bit more stable, making them less willing to protonate. This is all to say that to protonate again, in order to facilitate another deprotonation at this position, becomes much more difficult in acid. In fact, almost impossible in acid. If you have one equivalent of bromine and you add it to an acidic solution and then throw in a carbonyl of some kind, you will almost never get more than one bromination. So completely opposite, as we might have expected, right? Acid condition promotes monohalogenation and not polyhalogenation like we just saw. So let's say that I have that same ketone, but I do H3O plus in bromine. Guess what? I will only get one bromination. Okay? Only one bromination, just like that. Cool. So an acid, right? Base promotes the removal of protons over and over, or bromine promotes the removal of protons on and on until we get a polyhalogenation. In acid, only get that one halogenation and you move on with your life. Okay. Now, what's kind of interesting about this reaction is that if we do the base reaction on what we call a methyl ketone, so that there's a CH3 on the ketone, okay, then actually this reaction will continue forward. After one side completely tribrominates, right, we'll get a hydration event on the carbonyl, where instead of kicking off the hydroxide, right, we will actually kick off the CBr3 group, which forms CBr3 minus. I know this looks like a bad leaving group, but CBr3 minus is actually very acidic. It's about as acidic as hydroxide, just so I can kick off. And that carbon grabs that proton there, carboxylic acid, to form the carboxylate. Okay. So 3 sort of observations to kind of observe here, just so you make sure you're understanding this correctly. Okay. If you have a methyl ketone and you run this reaction in base, you replace CH3 with O minus, right? Because you get a tribromination on the side and then removal of that CBr3 group. Okay. If you do this reaction in acid, you will get a monohalogenation. Here's the cool thing. You will always be selective for the more sub side if you do this. Okay. So you get this selectivity. Reason for why, don't worry about it, just kind of accept it. Okay. If I have a molecule that's not a methyl ketone though, right? Base will just do polyhalogenation. So all those there. And then base will just add once, just like that. Sorry, acid, my bad. Now I'm just, be clear, I'm getting tired, so I apologize. But acid will just add once. Cool, all right. So gonna just have to move on from here just for the sake of time because I want to wrap up in about 30 minutes. Cross my fingers, right, that I can do that. But that's the halogenation. Again, if there's anything to really remember, it's just all of this here, right? Mechanism you can just kind of practice and have down. Okay, cool. All right. So on this, I mean, there's this question here. We have a methyl ketone. We have, I mean, this can be any halogen, right? It can be X2 here generically. It doesn't need to be bromine. But we have a methyl ketone. So we know that we're replacing that with O minus. Oh, oops. I did not mean to do that. My bad. My bad. My bad. I was just trying to. Okay, anyways. Sorry, my bad. I should have done that. Anyways. If I had this in acid, I did this reaction in acid, and I would get the monobromination here. I've actually done this reaction, so it's pretty cool. I know this works. So it's nice to have that personal confirmation, right? Now, let's say that this were like an ethyl here, right? If that were an ethyl, then we would get X here, X here, X here, right? In base, right? And if we're in acid, right, we would just get the X here because that's the more subside. Cool. All right. So halogenation, attacking a bromide, right? Go ahead and add that onto the enolate. That totally works. So what about if I wanted to add an alkyl halide, right? That should probably work. And for the most part, it can, right? RO minus can get an attack, can form the anion here. Okay. And so if we have an alkyl halide, like a primary one, right? Shouldn't be hard to believe that, yeah, we could get sort of like an alkylation event. And for the most part, you can. That is possible. Okay. A couple problems with this though, okay, in this class. In this class, alkylations actually suffer from the fact that, just like, alkylation in benzenes, you can get polyalkylation. It turns out that that's a possibility. Okay, so we might accidentally alkylate on multiple positions, which is very, very terrible. Okay. The other issue is that especially with aldehydes, we have competing reactions. So when we form this aldehyde enolate, turns out this aldehyde sometimes alkylates. So sometimes on the alpha position, we go ahead and we add an alkyl group. Other times, and most of the times though, we do other reactions such as the aldol condensation, which we'll talk about right after this. Okay, that's usually the most common reaction that comes out of the alkylation series. So how do we solve this problem? How do we end up alkylating on these positions? We use what we call enamine alkylation. And enamine alkylation is the following. Usually use pyrrolidine in these reactions, but you can form the enamine of pyrrolidine on a ketone or an aldehyde. Okay, as such. And then you introduce your RX group. Okay. Pyrrolidine is pretty good nucleophile, so have nothing to worry about there. Okay. That leaves us with the iminium ion, which again, iminiums are just nitrogenated carbonyls. So we're just going to add back that oxygen with water, and out we get is our alkylated position. This usually works really well, especially on aldehydes. Works really, really well on aldehydes. Okay, ketones not that big of a deal, but we're making it a big deal in this class, so we'll consider it also a big deal. Okay, cool. So you can also do this on ketones if you want to, which we can see in this question down here, right? Where the first step would form this. We get the CH2PR on this alpha position here, and then we get rid of the iminium, turn it, or we get rid of that enamine, turn it into a carbonyl. Sorry, did I draw that wrong? Oh, I did. Sorry, should be this. Well, I guess I didn't draw it totally wrong. I should have drawn the intermediate. So we'll have this, and this will turn into this, right? And then this will turn into this. Yeah, cool. All right, so that is the alkylation. And again, for aldehydes and ketones, this works. And in synthesis, just do it this way, right? That'll save you points. Okay, cool. Now, I guess one thing that might be worth considering is, right, what if I had a ketone that's asymmetric? Right, technically, there are two positions here that you could potentially deprotonate. That is true. And there are ways of getting around which position to attack, right? Kind of part of this goes into thinking about how we usually get alkenes at these positions. So for example, let's say I wanted the less sub alkene. What would we normally use? We would normally use a bulky base, right? Something that's very large, prevents it from attacking that more sub position. And there's a base for that. That's LDA. Okay, LDA, very, very basic molecule, pK of like 35. Again, for a molecule, for a proton whose acidity is about 20, right? 35, very, very sufficiently able to deprotonate this. We'll pull this off very easily and form the less sub enolate. We call this a kinetic condition. Okay. A much more milder and easier to access the more sub alkene with would be the hydroxide or the alkoxide series. Right, so RO minuses, because RO minuses, right, again, they are smaller, they're able to fit into tighter positions, and they can pull off these protons here, right, that are in these tighter spots. But most importantly, what the most important thing is that these bases are equilibrating, right? So this is a kinetic base, pulls off this proton instantly, right? Because it's 35 to 20. So this proton falls off rather fast. Absolutely no issue at all. But an RO minus, again, that has a pK of like 15. So in fact, actually, if I have RO minus, this is actually a weaker base than the proton that we're trying to pull off, or it's a stronger acid than the proton we're trying to take off. So in fact, it's actually really hard for RO minus to even pull off any of these protons. Okay? But when it does so very slowly, okay, and possibly pulls off this proton here first. So it probably pulls this one off first. Okay? Pulls it off, forms a less sub, right? And this is constantly in equilibrium because again, yes, this base can eventually pull off this proton, but this minus is not as stable as this one. So guess who just donates their proton right back, right? It's going to be that ROH. Because again, R minus is much more stable. So this equilibrating base forms an equilibrium between possibly this and eventually might take this proton here, right? But the point is, right, it's able to access this proton, right? Eventually it might come and take this, and it might take it might take a very long time, but eventually it will come and take this proton and it will form a little population of that less sub anion, or sorry, that more sub anion, right? LDA, who deprotonates immediately and just fucks off, right? Gets out of the way, will only ever deprotonate the less sub good of its bulkiness, never even talks to the more sub. The smaller base talks a little bit to both, right? And really what helps it do that, because maybe it might talk to this one a little more, make that mistake, is it's reversible, right? Because if it goes here, well, hey, guess what? ROH can redonate that proton and eventually it can go down here, right? Eventually it can, right? And when it does, right, it'll do it, a reaction will occur, things will be all right. Okay, so I'm not, honestly, I'm not sure how much Nasir really got into this idea of kinetic and thermodynamic bases, but I want to introduce this idea now that some things will attack directly and stay there forever, whereas some things will attack directly, come back off, and then reverse off into a much more equilibrating condition. Okay? So it's okay if all that stuff I just talked about kind of went over your head. To be honest, you have slightly inebriated Jim trying to explain it. So it's not going to be total. It probably doesn't make that much sense, but just want to get that concept in your head right now. Cool. Anyways, so there is a way to pull off less sub, more sub protons, right? If you want an easy way to remember it, right, just think about it this way. OR minus pulls off the more sub, LDA pulls off the less sub. So we'll call it there. I'll probably put a little note. And whenever I talk about kinetic and thermal bases, just kind of, it's okay to skip over that. I did a bad job explaining that, to be honest. Cool. All right. So we can alkylate. Again, go through the enamine and synthesis, or look out for this sequence, right? In predictive products is a very easy way to see it. This could also be a very good multiple choice, right? Is all she has to do, your test writer, is just write out this condition, right? And you just have to figure out which carbonyl matches. Okay, cool. All right. So the very last thing, well, not the very last thing, but probably one of the most important things that a carbonyl can attack and enolate can attack is another carbonyl. So this is the aldol reaction. So again, if I use RO minus ROH, right, this acetaldehyde will form small amounts of this anion here, right? Again, remember it's equilibrating. If you remember that conversation, it's okay if you don't. But when it does, again, this is looking for really any electrophile in solution. Why not use the electrophile we've been talking about all night? Another carbonyl, right? And so this anion can go ahead and attack here. If I kind of count my carbons, 1, 2, and 3, right? 3 where the attack is, it should form a 3-carbon framework where 1 will have the carbonyl that did the attack, right? 2 will just be this guy here, and 3 will be the carbonyl that we attacked. So we'll have an O minus, the CH3 group, and the H, right? So it's just like this, 1, 2, and 3. Okay. 1 also has, looks like an H here. So I'll just add it in just as a placeholder. Okay, cool. And so this can go ahead and capture proton. And what we get out is this here, right? We have an alcohol aldehyde species. The name of this is an aldol, okay, or a 1,3-hydroxy aldehyde. Okay, it's our aldol product. Okay, we call this an aldol addition, right? Because the enolate added onto an aldehyde. Many aldehydes can do this with itself, right? You notice that this is just attacking itself. Many aldehydes can do this, right? Just a matter of what you have available. So this guy could have also have done it, right? This anion here can just attack another one of itself. Again, sort of that 1, 2, and then 3, right? 1 being the carbonyl, 2 being alpha, 3 being the carbonyl we attacked. So we'll form that 3-carbon framework, right? This is always what your 3-carbon framework is going to look like: carbonyl, alpha carbon, and then alcohol. Okay. On, okay, these aldehydes, so this will be aldehyde like that. 2 will have a 1, 2, 3 carbon chain, so 1, 2, 3, and then 3 has a 1, 2, 3, 4 carbon chain, so 1, 2, 3, 4. Okay, there's our aldol addition product. Okay. Many aldehydes can do this, right? As long as they have the ability to analyze and just have another aldehyde in solution. Okay, but what's really important and interesting about these compounds is if you just do this reaction at room temp, right, where you kind of just cough on it, really, these compounds very easily dehydrate. Yeah. So, for example, this compound, base will take off this proton very easily. Okay. Oops, sorry, I kind of got ahead of myself there. Oops. Okay. And then this anion can go ahead and kick off this hydroxide, forming this pi bond here. Okay. You can do the same with this one as well. I'll just kind of do it. Actually, I guess I'll just do it the arrows correctly. That way none of you can blame me for any bad arrows. Okay. This style of elimination where we form the anion first and then kick out the hydroxide or the leaving group is known as an E1CB. So E1CB, by the way. Again, I don't know if you guys learned that, but it's just good to know it. Okay. But these dehydrated compounds are what we call alpha beta unsaturated carbonyls, or in this case, aldehydes. Okay, and these are the true product of aldol condensations, or the attack of an aldehyde enolate on itself. Okay, so one thing about this compound that kind of eludes people is how in the world do we use an OH minus leaving group? Right? Didn't we talk about this whole year not to do that? And that's true, right? You generally don't want to be kicking off OH minus, but turns out that if we have some kind of trade-off, like extra stability, OH minus is not that bad of a leaving group. I mean, we can see here, this is a conjugated system, right? Conjugated systems are actually pretty swell, and can, again, act as an energy trade-off in kicking off something that's unfavorable to kick off, but end up resulting in a lower energy system. Okay, so that's major reason why we see these hydroxyls getting kicked off. Shouldn't really disturb you too much though. It's okay, it's totally fine. Okay. So, now, as you can see in this aldol mechanism, it's, there's quite a couple steps, and you can always just go ahead and draw it. So I imagine on the exam you have 2 hours, you might have enough time to, draw out the product and do the mechanism to make sure you got it correct. But again, I like doing these in ways that make it very fast and very quick, and in ways that you don't have to worry about it. So there is a trick to drawing these very quickly. Okay. And so that trick involves, like, for example, we can do something like this. So again, best way to kind of recognize this, like a self-aldol, like we've done with these two, is you see an aldehyde, or we'll talk about this in a second about ketones. Ketones can also do this too, but aldehydes were the original. I mean, that's the reason why we call it aldol, right? It's originally for aldehydes. But aldehydes originally is where we saw with these. A way to do these very quickly, recognize them as base and heat and just an aldehyde, right? Only thing this can do is do an aldol reaction itself very quickly, right? On the alpha carbon of your aldehyde, right? Because again, these are alpha reactions. You just want to draw a double bond, and then the 2 groups on the aldehyde, or another way to think about it is everything but the oxygen on the aldehyde is what you want to add to this position here, just like that. Just like that, if that makes sense. Okay? So that's the very quick trick. So I'm going to put it this way just to, so everything doesn't kind of clump into each other. Okay, but that's your aldol condensation, very quick and fast. Okay. You can also do it on these guys too, just to prove that it worked on those, and just nitpick an example that it would work on. But if I were doing it on this, right, all that alpha carbon, right, double bond, doesn't matter which direction, I'm just drawing it down because I like doing that. And then just everything but the O, right? So the two groups right here. So the methyl and an H. There you go. That is your trick right there. Okay. You can also do on this one too. Okay, double bond on the alpha, and then the two groups on this aldehyde, which were the 4 carbon chain and the H. Now, a couple of you might be thinking, how do I know when to make them alkyl chains match and I don't? General rule of thumb, you want to draw the alkene that's most stable. So, or you generally want to draw the alkene that's like less sterically hindered, I suppose. So you can draw it this way. To be honest, you guys don't know how to control which way the alkyl chain goes. So all of you can kind of draw whatever you want, and it should be correct for the most part, and it wouldn't be a problem. That's kind of how it works. So, I mean, you could do that if you wanted to. So if you drew it this way, that's totally fine, right? No big deal. But just generally, if you can, just try to make sure it's like the less steric version. Again, you guys don't have control over this, so it's like not that big of a deal if you get this right or not. Cool. All right, well, that's how you do aldol condensations very quickly to make these enone type compounds, okay? And so aldehydes reacting with themselves can make these really easily. It's totally fine, right? No big deal. Ketones can also react with themselves. It just requires much more rigorous condition, right? So if I had like this ketone here, just kind of have to boil this for a long time. Right, this will form an enolate that could attack itself. Right? I mean, you can go through the motions if you wanted to of like drawing out this product here, right? Protonating it and then eventually dehydrating it. But simple problem, right? Alpha carbon, double bond, and then in this case, the two groups is just the ring. So we just add the ring like that. So you can do this. Ketones, though, for the most part, they must be heated, and as a result, will always go to the enone product. Back here, I guess I shouldn't have deleted all that. Back here, you actually can stop at the aldol, but you have to be at like -78, like very, very low temperature. I think in this class, like below zero degrees is where it would stop at the aldol. So below 0 degrees is where it would stop here. But anything higher, like room temp, it's gonna go straight to the like no questions asked. You don't have to like look at it or heat it up too hard. In fact, I've seen some aldols proceed at like -15, -10. Like it's a very favorable reaction. Okay. Just very much so with the ketones, right? The ketones, very, very hard to stop it at the aldol. Or at the ketol, I guess. Usually we'll just have to go straight into this here. Okay, cool. So I can add aldehydes themselves, I can have ketones themselves. Can I do any kind of mixed reaction? Because I doubt every molecule in the world wants to be symmetric, right? Maybe I want to have some asymmetry. So for example, maybe I want to take this aldehyde and couple it to this one here. And the answer is, kind of yes, right? If we look at this reaction here, we have two aldehydes that can enolize. So two aldehydes that can become enolates, and then two aldehydes that can attack each other. So I call this A and I call this B. Guess what? Doing this reaction will give me a mix of AB, BA, AA, and BB, right? Because both of these can enolize and attack each other, right? Enolize, attack, analyze and attack, or analyze and attack itself, analyze and attack itself. So, I mean, this would be great practice to try and draw all these products. We'll draw a couple, like let's draw the AA product together. Right? AA would mean that, one of these attack this guy. So we'd have double bond here, and then we'd have like an H and an ethyl, right? AB would be if A analyze and attacked B. So double bond here. Now we have, instead of an ethyl, we have a methyl and an H, right? Practice drawing BA and BB on your own, right? That's a good practice. But generally, two carbonyls together like this, not a very good idea. So what we do is use something called non-analyzable carbonyls, carbonyls that don't have alloprotons, so they always exist as an electrophile. For example, benzaldehyde. Benzaldehyde's a very good example of this, right? This guy has no protons, so if we think about who attacks who, right, this guy will always attack this guy, right? There's never an opportunity for this attack to happen. It's impossible, right? No alpha hydrogens. Or I guess what I should do, that was kind of confusing way to draw, but this doesn't exist, right? So we know that this will always attack here, right? This alpha carbon attacks here. So what we get, double bond, H like that, right? That's always going to be our mixed product. Okay, so very successful mixed reaction there. I believe there is a mix on this exam. Yeah, so you can see here we have a ketone, we have an aldehyde, right? This aldehyde is non-analyzable, so we know that this ketone, right, will go and attack like that. So then now B kind of confirms to us that, oh, we can do mixes between ketones and aldehydes as well. Just, again, make sure one is not analyzable. Generally speaking, ketones attack aldehydes. That's just how it works, okay? If I want to just draw a nitty-gritty rule for this, right? Aldehydes are just way more electrophilic than ketones. So, ketones just have an easier time attacking aldehydes. So again, double bond on that alpha. And then I'll put H here, and I'll put the phenyl group here. Okay, and there you go. That's your aldol condensation product. Okay, cool. So aldehydes can attack themselves if it's just aldehyde and base. Ketones can attack themselves if it's just ketone and base in a lot of heat. Right? Aldehydes can attack other aldehydes as long as the other aldehyde has no proton. You see down here. And ketones can attack other aldehydes. Right? We can mix ketones on aldehydes as long as aldehyde has no protons. A couple of different examples of these aldehydes that don't have these protons. Another one is formaldehyde. Right, formaldehyde is another one of these guys. Right, terbutyl aldehyde. Another example. Right, anything where this is completely full, right, has no protons. What's another good one? Yeah, I don't know actually. These are I guess I'm a little too tired right now, but if I can think of more, if anyone can think of more, just ask me, fine. But essentially anywhere where there's no alpha hydrogens, zero alpha hydrogens, right? That's what we're looking for. Okay, cool. As always, intermolecular reactions exist, so always be on the lookout for them. The dialdehydes are pretty simple, right? One attacks two, so 1, 2, 3, 4, 5, and 6. This will be a 6-membered ring. One attack two, so 2 is where the OH will be. We'll have an H for the aldehyde. 3, 4, 5, 6, if they have anything, add them in. 1 has another, like it has the aldehyde kind of hanging out. Okay. This will, if you count it my way, it always dehydrates between 1 and 2. If you don't count it my way, right, it always just dehydrates towards the alkene, right, to form that conjugated system. Okay. So dialdehydes always look something like this because it's always between the two carbonyls that the reaction occurs, right? The enolization and the attack occurs between the two carbonyls. Okay. So you can imagine that you could possibly do this with a ketone as well. Same thing, right? All that changes here is that on the outside here, there's just a ketone. Okay. Where things get a little different though is when we have ketone aldehyde mixes where instead of attacking between the two carbonyls, you're going to attack from the outside of the carbonyl. What do I mean by that? I mean it's like this. Okay, where, oh wait, there we go. I mean like this, where the attack can happen like that, where instead of attacking from between the two carbonyls, attack from outside. So 1, 2, 3, 4, 5, and 6. So we get a 6-membered ring. Right? 1 attack 2. So 2 will have our OH, their methyl there. Oh, sorry, with our H there is what I meant to say. 3, 4, 5, if they have anything Enamine. 6 is going to have our carbonyl because it's numbered 6. Okay, and so this is our molecular aldol. Okay. Again, alcohol will always dehydrate towards the carbonyl, and so that's our enone there. So you can kind of see how these two molecules might differ, right? Where the carbonyl is embedded in the ring and one where it's hanging off the ring. Okay. Cool. All right. Shoot. So we've hit the 2-hour mark. I guess we'll just have to start speeding this up. Okay, cool. I mean, we'll cover whatever we can anyways to review, like doing the problems itself. Okay, cool. So do we see any example of this other than that? Yeah. So actually C is a sort of hidden example of this. Recall that O3 cuts double bonds and turns them into carbonyls. We can see that C is just a hidden aldol condensation. Okay. We have a dicarbonyl compound that's reacting in base, right? Again, ketones attack aldehydes, so we just got to figure out, is it 1, 2, 3, 4, or is it 1, 2, 3, 4, 5, and 6? Definitely going to be that there. So 1 will attack 2 here, 3, 4, 5, and 6. So we'll end up with a 6-membered ring here. Right, where 1 attack 2, 3, 4, 5, and 6. Right, on 4 was where we had that sort of connection to the other ring. So just kind of add that in. Okay. So look out for these intermoleculars. Pretty cool problems. Honestly, these are pretty cool problems. I don't see any others on here that did this. Any on here? No, looks like I didn't really. Oh, yeah, F. F is also another intermolecular, right? Ketone attacking ketone. So either it's 1, 2, 3, 4, 5. Well, now we know for sure, right? 1, 2, 3, 4, and 5. That makes a 5-membered ring. Okay. I guess I've also said this in my head too. 5 and 6 are the rings you want to form, right? If you don't get 5 or 6, you want to try the other way. So let's say this didn't give us 5 or 6, then we try from here, right? The other alpha carbon. Okay, it'll be a 5-membered ring. Right, 1 attack 2, so 2 will have our OH, and also a pH. 3, 4, 5. 5 has a carbonyl on it. Okay, and then 1 has another pH sticking out. Okay, again, OH will dehydrate towards the carbonyl. So we'll form this here. This is actually a drug precursor, I think. I think that's where I got that idea from. It's a drug. Okay, cool. All right. So unfortunately, I'll have to call it there for aldol because we have hit the 2-hour mark, and I do want to hurry up and finish this. So we'll have to get into the last bit of material here. So I apologize for all the rushing. So enone compounds, right? Or these alpha beta unsaturated compounds, what's so special about them, right? Well, one, again, they're stable because, we have these conjugated systems, right? So we know that the energy kind of system is very low. It's very stable, very nice. So much so, in fact, actually, you guys might remember I drew this molecule earlier, and I kind of hesitated to say that this was stable in acid or base. And the reason why I did that is because, well, in fact, actually, in acid or base, these kind of molecules were isomerized. So again, in OH minus, you can pull off this proton. To form this conjugated species. And then this conjugated species will go out and attack a proton, right, probably from that water molecule made earlier. And they will conjugate themselves. So these systems here where the alkene is like one away, quote unquote, from being an enone, right? A conjugated system. These guys will isomerize very, very quickly in acid or base. In fact, actually, one of these questions does that, right? If we look at all of these, we notice down here, there's a ketone where this alkene is just one away from being, conjugated to the ketone. Guess what? In base, that's actually what happens. So the first part of this molecule does in fact isomerize into this here. Okay, so that definitely is the first part of this reaction. There's a second part though. There is the second part. Okay. So first thing about these systems is that they're very stable. In fact, actually, if the alkene is one off, they will isomerize to form these systems. The other is that these systems are actually electrophilic on two carbons. So we know that the carbonyl carbon is electrophilic, but via resonance, we can see that the beta carbon, right, or the farther away alkene carbon is also very electrophilic. So alpha carbon, beta carbon right next door, right? That beta carbon, very particularly electrophilic. Okay, and so nucleophiles, when they attack these enone systems, actually have two positions to attack. They can either attack, this is different color. They can either attack on the carbonyl carbon or on that beta carbon. Okay, so what determines one over the other? Well, it's really easy to just remember what attacks on the carbonyl, or what we call direct. Okay, R minuses, so like RLI or RMGBR, will exclusively attack on the carbonyl. Call it a day. Okay. NAPH4, LiALH4, and exclusive attack on the carbonyl. Call it a day. The third are ammonia derivatives. All of them have the same look in that they look something like this. So these hydrazine derivatives, where we kind of like an NH-NH2, they will form amines on the carbonyl carbon and condense out. Call it a day. Okay. Everything else in the world is going to attack on the beta carbon. So OH minus, beta carbon, RO minus, beta carbon, RS minus, beta carbon, right? X minus, beta carbon, CN minus, beta carbon, enolates even. So enolates will attack beta carbon, enamines will attack beta carbon. So many things, right? The list just goes on and on and on. But the most important thing is that as long as it's not one of these three compounds, we attack on the beta carbon. Okay, so let's say that I have this here, and I do a reaction with, let's say, OH minus, right? OH minus will attack on the beta carbon. And then this will protonate with possibly some water in solution. Okay. And we'll get this 1,3 compound. Okay, so this 1,3 nucleophile carbonyl compound, right? Let's say that it's sulfur. Again, the attack is the same. Right, and then this will go out and attack a proton, probably from another sulfur molecule or something. And then we'll get this 1,3 compound with the ketone, right, or with the sulfur. Okay, I mean, this could be really anything. I mean, if it were HX, guess what? It's just X there. Okay, so a new, very important identity to recognize in synthesis potentially is this 1,3 relationship, right? Where from the carbonyl, right, starting from the carbonyl 1, 2, and 3, or you can also think beta to the carbonyl. Beta might be the better term, honestly. It's a way better descriptor. But beta to the carbonyl, there's some new transformation, right? Something worth thinking about. Okay. Now, let's say that we do a reaction again with like CH3Li, right? CH3Li, like a Grignard, right? We actually might even have that on one of these pages here. But again, that's the nucleophile that attacks the carbonyl. So this, in fact, would attack here. Okay. If I did a reaction with like lithium aluminum hydride, very simple. And that would be like an H adding here instead. Okay. So enone systems, it's like a 50-50. But if you understand these rules, it's even higher than a 50-50. It's like an 80-20, to be honest. It's, in my opinion, a little difficult to get these hard or get these wrong. Cool. Now, one last nucleophile that's worth talking about then is, okay, is there any way to add a Grignard reagent at that beta position? And there is. R2CuLi. Okay. Now, don't get this confused. You see the R2, and like, don't let that trick you. Nothing is adding twice here. Let me just get rid of all this stuff here. So we have this here. R2CuLi, right? R2CuLi is a very interesting organometallic that does in fact attack on the beta position. So one of the R groups, not both of them, just one of them, will add on to that position there. But what's really interesting is that R2CuLi is not protic, right? It's not like the rest of these where you might have some proton source to quench this enolate anion. Once you add on R2CuLi, this anion has to be quenched. So it can be quenched by a proton. Put an H there, but you can also quench it with other things. For example, an alkyl halide. So you can potentially get two alkylations, alpha and beta, to a carbonyl if you quench with an alkyl halide. Okay, you can quench with a halide as well. That's also possible. Okay, cool. So this sequence here, I like to call this Gilman coupling. Not that that's actually the term, it's just what I call it, just to refer to it very quickly. But the idea is, if you have an alpha beta unsaturated structure, right, the R2CuLi always adds to the beta position. So this is the beta addition. The Rx that follows up adds to the alpha position. Right, so this will be your first one. I'll call this all prime. Your second one, right? And so alpha beta branching, right, in synthesis can be explained by this type of coupling process or by this type of reaction. So if at the end of your synthesis or at the end of your end product, you notice a carbonyl with branching at alpha and beta positions, consider the fact that you might have done this sort of R2CuLi into Rx sequence. Okay, cool. All right. Sake of time, we do have to move on though, so I apologize. I know I've been rushing a little bit since we started enolates, just because, I don't want this to be more than 3 hours, to be honest. Cool. All right. So last thing we'll talk about is the Michael edition, and we'll wrap it up on the quarter, and then we'll just go through the rest of these problems. Make sure we know everything. Okay. Cool. But anyways, last reaction is the Michael addition. Okay. And so that's when you take a carbonyl compound and add it to the enone. Okay. These two together are going to make an enolate. Right. And then this enolate, I go ahead and add into the carbonyl. Now, easiest way to solve this is that whenever you do a Michael addition, you're always going to make a 1,5 dicarbonyl. So this will always be the case. This is 1, we can call this 5. 1 has a methyl on it, right? 2, 3, and then we can say 4 or 5, right? 5 has a methyl on it. So this is what this looks like. Okay. This is what's going to be the structure for every single Michael addition, this 1,5. Okay. or at the very least, it'll have this structure here. And then depending on what groups you have, you might have something at one, like carbonyl on the carbonyl. If it's ketones, there might be something there, right? If it's anything on 2 and 3, you can add it in. It doesn't matter. Okay. What's really important though is that if we have access to these like sort of outside carbons, or these carbons that are outside the carbonyl, if there's, hydrogens on those carbons, like at least 2, right? You can get an intermolecular attack to form this here, a cyclohexenone, which if we kind of number this 1, 2, 3, 4, 5, and 6, that would just be 1, 2, 3, 4, 5, and 6. Okay. This is known as the Robinson annulation. And what's really important is that this shape here, this particular cyclohexenone, is always indicative of a Robinson. So in the synthesis, if you ever see something like this, right, where you have a ketone with an alkene, right, and are both embedded in a ring, that is a Robinson. That is the key signature for a Robinson. Okay, this is the result of a Michael addition into an intermolecular aldol. Okay, and so you can very quickly degrade this down. Okay, into, well, first you can degrade it into these 2 pieces, and then degrade this down into oh wait, where did I mess up? So you can, oh yeah, so you can degrade into these 2 pieces, right? And so from here, you can kind of degrade in 2 ways, possibly the easiest way, right? You can either make the enone here and say, you break this bond here. So you can make the enone there. Or you can say, you make the enone here and then break this bond here. Right, which I think I like this one better, right? That looks a lot better. Okay, cool. So how did I break those down, right? How did I make that so easy to do in like a second? It's very simple. On an enone, label alpha beta, cut down that double bond there. Right, so we get to here, okay? Alpha stays the same, beta, you just add a carbonyl. And that's how you break down any enone. Doesn't matter if it's the result of a Michael, doesn't matter if it's the result of just some regular aldol, right? All those aldols that we did earlier, same thing, right? If I just alpha beta, cut down the middle, guess what? It's all it is, right? Alpha stays the same, beta just add a carbonyl. And there you go. That is your aldol condensation. Okay. From here, we notice that this is the 1,5-dicarbonyl, right? 1, 2, 3, 4, 5. So we know that we can cut this even further into a Michael, except an enone and an enolate. Again, kind of 2 ways you can do it. Either you can say the ketone here is the enolate, but that would require breaking the ring, which I don't like. If I call this the enone acceptor, right, or the enone Michael acceptor, and I break that bond there, this looks a little bit nicer and much more feasible. Okay, cool. All right. Well, with that was all the material speed ran in 2 hours and almost a half. Again, my sincerest apologies that for chapter 18 we got really late. I got really lazy, to be honest, just to finish the material. Again, hopefully you guys have been, doing a much more diligent job than I have in getting up. But that should be a pretty good, wake up for the material and what you need to know, and for the most part, stuff that's going to be asked of you. Time to get into these exams, right? Just to finish these out. So, were there any of these that we kind of skipped over? Yeah. So, we skipped over this first one. So, I think now we can do this first one. Right. This first one is a diene alkene. This is just Diels-Alder initially, or it'll actually be the other way. Yeah, that makes more sense. Right. So we'll get the this here. Okay, cool. So we'll get the Diels-Alder there. And then the second step, we have base, and we have a Michael acceptor, right? Or an enone, like we just talked about. Base and enone means that we have some nucleophile that's going to add into that beta position. Remember this position only if it's those 3 things, right? RLI, RMGPR, NABH4, LiALH4, or those hydrazine derivatives, right? But it's none of those things, right? What we have is an aldehyde. So we know that enolization is going to occur. We're going to do protein at that position there. And on this guy here, right, it's going to get attacked there. So we're going to form 1,5-dicarbonyl. Okay, so 1, 2, 3, 4, 5. 0,15-dicarbonyl. It's a methyl on here, so we'll add a methyl there. Okay, and then again, as long as we have this sort of arm on the outside of that 1,5-dicarbonyl, we know that this arm can attack on this guy here to do a Robinson. So we can form the body of that Robinson if we wanted to. So 1, 2, 3, 4, 5, and 6. And counting is up to you. I'm just gonna count this as 1, 2, 3, 4, 5, and 6, right? Oh, actually, never mind. I can't do that. I have to count it particularly, right? Because this carbon here, 3, is like the spiral carbon. So this has to be 3. So I apologize. It's wrong. So 1 attacks 2. So 2 will be where our 8 always will be. 1 will be, will be attacked. So 6 will be our carbonyl, right? Again, we'll always dehydrate between where the alcohol was and the carbonyl. So we'll get to here. And this is our final answer. So kind of an interesting Diels-Alder into aldol condensation or Robinson annulation, really. Yeah, cool. That's that one there. D, we have CH3Li initially adding into, and that's a direct addition. Initially, it will add into the carbonyl carbon, not the beta carbon, right? So we'll form this here. Right? And then the alkene can react with Cl2, kind of a really cool tandem reaction, right? Because Cl2 will form the chloronium, and then this guy will go ahead and open it up right next door. So kind of a complex reaction, actually. We'll form this sort of epichlorohydrin oxide. Okay, cool. All right. So those are the reactions there. Any other ones? No, that's about it. So that was the Pudic products for the first section. For the second section, we just did this one. So for this one here, right, you guys might remember what we did was we replaced oxygen with 1, 2, 3. So 1, 2, 3, carbonyl here. And we'll have this there. Notice how this Wittig reagent is a very interesting one. It helped us make an enone. So enones are not only accessible by the aldol, you can also make them by Wittig reactions too. Pretty cool, right? Just gotta, again, add that ketone as the conjugated Wittig, right, into the ketone there. So that's one way to do it. Another way to do this is to actually do the halogenation reaction. Right, in acid, and then use a weak base like pyridine, or you can use bicarbonate, and that will do a soft E2 to form the enone as well. So 2 different ways. I know there's a couple different ways in your notes on how to do this. So, be sure to look in there. Again, I tried to just cover the most important things and cover exactly everything I could have, but things to consider. Okay, cool. So we can do that. And then again, we have that C2CuLi reaction. Oh, I guess I forgot here to put H plus. That's my bad. But CuLi will add it at the beta position. So I'll just kind of draw a condensed version of this. Right, but we will have this add in here, that CC double bond, right, adding there at that beta position. All right. I think the rest of the reactions we did cover, though. Oh, we didn't cover the last one. So the last one I mentioned that we do get that isomerization. that alkene's just so close, right? So we get that isomerization. And then, right, guess what? We're in base, so this can protonate, and that can add in. So a cool little tandem reaction. This was actually featured in a total synthesis. I just don't remember which one it was. I'm having a hard time remembering which one it was, but function should not be there. It should be like here. 1, 2, 3, 4, 5. Yeah, it should be 6. Cool. Yeah, I forget which total synthesis this was used in, but that was used like a synthetic technique by an actual chemist. Cool. All right. Again, with these 2 exams, it's not totally exhaustive on what you can ask, but definitely it's new material. So practice it. A lot of practice. In fact, I actually have a practice sheet that I can probably throw in that has more of these problems you can practice. So I will do that as well. And I'll throw the answer key into just now, just because there's only 2 more days. But yeah, practice as much as you can. Use ATC. I just, only had enough time to make 2 of these exams that could only feature so many reactions. Okay, cool. All right. So let's actually just go into synthesis mechanisms. We talked about most of these, so you can probably figure them out. Don't stress too much about them. Well, I guess you should stress, but healthy amount. Just practice them and understand the mechanism, the arrows, and all that. I think maybe just some good thing here to do is just practice predicting. So MCPBA, Baeyer-Villiger with an aldehyde, that's going to make carboxylic acid. This is an aldol up here, right? Ketone base aldehyde, so aldol, right? Alpha carbon of that ketone, going to add right, H, and then the ring with the NO2 on it, right? So just practice that. For this one, it's deoxygenation, so just get rid of that. Right, HH. And then this one, again, remember, you can think of it as a ketone reacting with 2 alcohols or 2 alcohols reacting with a ketone. The same thing, right? Just different perspective. So it'll form that acetal carbon in between those 2 alcohols. And there we go. Yeah, cool. Kind of looks like a sheep, actually, if you think about it. Just a little bit. I don't really know what sheep look like, to be honest, but whatever. It's a bad sheep. Cool. So let's just get into the syntheses, and then we'll get into the multiple choice. Okay, cool. So these syntheses, again, were pretty hard, not gonna lie. Pretty intense. But again, it tries to cover all the concepts that you need to know for new stuff so that, you know, you guys have a better time with it. Let's start with the first one. So I mentioned this, we just talked about this. When you're looking at your end material, look for patterns, things that shapes that you can very pinpoint very closely into what they had to be. I see that cyclohexene, right? The thing that we just talked about. That if you see it, it's a Robinson annulation, right? Or some type of, you can at least guess it's some type of Robinson annulation. So I'm going to go ahead and guess this is a Robinson annulation. The way you break that down, right? Alpha, beta, cut right there. Right, so we'll have this here. Again, alpha doesn't change. On beta, you want to add a carbonyl, right? And then from here, we see that we have a 1, 2, 3, 4, 5 dicarbonyl. 1, 5 dicarbonyl is the result of a Michael addition. So ask yourself the question of, do I want the enone here? And I cut off this guy. Or I guess I should have done all that. But ask yourself, do I want this and this as my donation or as my partner that I say that this adds into here? Or do I want to say that this was my enone, right? And I broke that bond and connected these 2. I'm gonna be honest, this looks complex as hell. Like, how in the world am I gonna build this whole thing from this? But I feel a lot more confident. Okay, I don't know why all this erased. So I'll just redraw it. But I feel a lot more confident if I say that, hey, I think my enone is this guy here, and I added this enolate in like that. Okay, so I like this connection better, especially when I notice that the resulting ring, right, when I do this cut, so when I say that, hey, I think that this came from the Michael into Robinson annulation of this, right? I noticed that this is a cyclohexene. This guy's cyclohexadiene, but cyclohexene is the main culprit here, right? Like if I had this, this is a main indicator of the Diels-Alder reaction, where across from the pi bond I cut off, I get this diene and this alkene or this dienophile, right? Same thing with this here, right? I'm getting that same vibe. It's just that this is a cyclohexadiene. It's like hexadiene. So there's two alkenes, so it's not totally obvious which one is the dienophile, which one's the diene. But again, use the EWG to guide you. EWG is always a dienophile. So I cut on this side. When I get out, it's going to be this here. And again, if I form a hexadiene, that means that my dienophile is an alkyne. So we use this propargyl aldehyde as our group here, but we form this diene. And so kind of just draw, don't want to draw it like that. Let's draw it like this. So now I've kind of reduced the complexity of 3 rings into 1 within 2 steps. Okay, cool. So cool little Diels-Alder into Robinson annulation there. Now, to go from here to here, a couple different approaches. Main thing is that we have a carbonyl that's adding carbons. Right? We have a carbonyl that's adding carbons. One reaction in particular, right, that does this, it's the Grignard reaction. But remember, Grignard forms alcohols. So I'm thinking that this pi bond here, where the carbonyl used to be, comes from an alcohol, right? We just use a dehydrating agent. Now, if you want to be very posh, you can use POCl3. I mentioned it very briefly a second ago, but very likely you guys just want to do this, right? Just use that, that's fine. Okay. But now you can kind of see where this could come from, right? It's just get rid of that. You can see that all we're adding in is here. On the key, you'll see that I used a couple different methods of doing this. I just did that for those of you that just like to brute force things and or have different ideas as to how things had happened. Really, I guess the least resistance pathway is to say that you added the final Grignard in directly. You can do that. Could have also went the alkyne pathway into some kind of hydrogenation. That works too. It's really up to you. I don't really care. But this is, for the sake of just finishing right now, we'll just stick with this pathway here. So we add in the Grignard, right? Dehydrate to the diene, do the Diels-Alder, and do our Michael into Robinson. Okay. And then just to kind of remind you guys, right, this is what the product looks like. Or this is like the intermediate for this step here. Okay, cool. So what is this meant to teach you? Well, one, it's supposed to incorporate all the concepts from the quarter, right? Starting from all the way from like chapter 12, 13, right? Into 14, all the way into now, right? To remind you of all these things we can do. Other things to also get you comfortable on cutting, doing those Aldol cuts, right? Those Robinson cuts, the alpha beta cuts. Okay. Very, very important skill to have. Cool. All right. That's the first one. Second one is a bit of a killer. It's a bit of a killer and definitely very difficult because, I mean, the way you see this acid here can kind of throw you off here. I'll be honest, I could have wrote this nicer. I definitely did not write this in the most friendly way possible. Yeah, this is not the most friendly written synthesis here. Okay, but it is meant to serve to teach you something. So, in fact, actually, to make this a bit more useful, let's actually ignore the acid for now. I actually want you guys to just focus on the ketone. Okay, this synthesis here is just an aldehyde into a ketone. And so we gotta look at it 1, 2, 3, 4, 1, 2, 3, 4, right? 4 carbons, nothing really changed. All that stayed the same. So all I'm doing here is I'm sort of sliding the carbonyl, sort of moving it, right? I'm just shimmying it down from the 1 position to the 2 position. Okay. And so if I think about concepts from all over from this order, what's the functionality that lets me functionalize vicinally, right? Because this is vicinal, right? 1, 2, 1, 2. It's vicinal. So sorry about that. Anyways, like I was saying, 1, 2, 1, 2, right? Vicinal. What's the functionality that controls vicinality? The alkene. So in this synthesis, really the first important thing to recognize is that we want to functionalize the alkene so that we can slide over to that 2 position, right? Because that's what the alkene allows us to do. You can also argue an alkyne as well. I could see that. I'll accept that argument because you might think, oh, alkyne is like the alkene, but it functionalizes directly to the carbonyl. I like that idea, actually. I think that's also one of the key too, now that I think about it. So you could say, oh, this is an alkyne, which comes from the alkene, and the aldehyde we eventually turn into the alkene. Okay? So let's just work. I mean, we can work on this part, right? How do we get alkenes? Well, bromides and alcohols, right? Elimination of those. I can get an alcohol straight from this, just NaBH4. Right? And I can do a dehydration here. So I use NaBH4. This, I'll just use H2SO4 delta. Right? From here to here, right? That's just the Br2 into NaNH3 sequence. Right? And then I could do an oxidation. Oh, yeah. So like, well, I guess not really an oxidation, but I can do a hydration. That's the better term. Right? I can do this here. Okay? That totally works too. So it's accessing that vicinal functionality that functionalizes that next door carbon that allows you access to the ketone. And you can imagine this actually works in both directions, right? Like I could reduce this into the alcohol, again, form the alkene, go to the alkyne here, and then go to here, right? That's totally possible. So you have the ability to slide. That's kind of the point of this question, is for you to notice that you could do the slide. Okay, so that's the part there. Where this gets a little bit trickier, right? So outside of just forming the ketone in the next position, is then adding in this new functionality. So I'll just put here the group G. So adding this new group G, suspiciously beta to the carbonyl. Beta to the carbonyl. What's the functionality that adds things beta to the carbonyl? We want to form an enone, because in the enone we can accept something on that, on that beta carbon, form that beta relationship or that 1,3 relationship. So how can I turn this into this? Well, obviously I don't want to do an aldol, right? Aldol will add extra carbons, and I don't want to do that just quite yet. Okay, so what I want to do here then is going to be using the bromination technique. Right, where we brominate and then we eliminate. And remember, if I do this at acid, I get the mono. Right? I get the monobromination. And then if I use like pyridine, or if I use, bicarbonate, I get a very mild, soft, elimination. Okay. And so now I can add a group onto that beta position, right? And nucleophile is that beta position to form that 1-2 relationship. Now, in this particular question, what I wanted on the beta position is that CO2H group, okay? Which, I mean, we haven't really met a group that's like an anionic CO2H, but there was a reagent I mentioned very briefly that you could transform into a CO2H. That was the cyanide, right? Cyanide you can add here, right? Onto that beta position nucleophile, then you can turn that into this here. Oops, sorry. Oh, but actually, that's really cool. We can actually do this. Didn't even think of that. We can actually reduce the system totally and form this, I suppose, which would form, 1, 2, 3, 4, 5. Oh, no, 1, 2, 3, 4, 5, 6. Yeah, it's a little too far. I was thinking maybe like closing this into a ring or something, but well, I guess you could do like an oxidation here, like a Jones or something. That way you get the like the ketone, and then this would close something. Yeah, that would close for sure. You could close that for sure into it's like an imine actually. Ooh, that would be oof, man, that would be a killer. Like turning like this into this. Ooh, that would be a killer. That's a cool one. I like that. I like that. It's a nice number of steps too, right? From like here, like 1, 2, 3, 4. It's just lithium hydride. 5, 6. Ooh, yeah, I like that. Well, really, this isn't. Oh, it's PCC. Yeah. Okay, that's a cool one. I like that. So I'll write that down at the extra problems, I guess. Cool. All right. Well, that's that one there. I know this one was a little bit confusing, but hopefully this helps make more sense. This was also on my exam. That's why I remember it. Or a version of this was. It wasn't exactly this. Like it wasn't exactly with the C. I added this part here to make it harder. I think mine was just I forget what was on this carbon here, but it was something like that. Cool. All right. We go to the next one. So a phenol is something we talked about a little bit in this class, but to kind of put into context, 17, 18, right? Try to think of reactions that an alcohol is involved in. For example, you can kind of protect these guys, right? With acetates or with ethers. Uh, None of the reactions on the ring are really concerning here because again, nothing is transforming on the ring. So we don't really care about what reactions we can do ortho-para. So probably we care about what's going on in the oxygen. If I had to look at either one of these two, maybe stare at for a little bit, maybe one of these seems more important than the other. That might stand out. We have an ether, we have an ester. Ooh, we have an ester. Maybe something about the ester stands out, right? Because we just talked about how, so getting rid of this would be like NaOH, right? That's what we learned. But maybe an ester is something we like talked about. We can make it very selectively now from a ketone, which we can add with Frey-Crafts. Okay, so very cool way. I mean, in this class, we kind of talk about how we have no access to these phenols. Well, turns out we actually do have access to phenols. It's just not until the end of the quarter, until we learn MCPBA, right, that we could do this. Cool. All right. Cool reaction. So first exams worth of syntheses. Hopefully those were insightful. Again, hopefully they taught you what to think about and at least have some extra ideas. Let's look at the second syntheses. Okay, cool. Let's start with this middle one actually, because we just talked about esters and we see esters here. So, I mean, I would be kind of an idiot not to just unesterify this, right? So I know this is MCPBA, right? So let's see, 1, 2, 3, 4, 5, 6, 7. Both these rings are 7, so that must mean that before these reactions there were 6. Maybe they were 6, something like that, and like that. Okay. And so now what do I have? I have this diketone system where if I kind of look at the beginning, I can kind of see where the beginning came from, right? The methyl kind of helps me track it. Right here, right? That methyl really helps me track that, okay? And I notice that this carbonyl is lost, but what comes in its place? A six-membered ring. Okay, now two kind of ways to make six-member rings, right? There's the aldol condensation, intramolecular, or I guess really the Robinson annulation, or there's the Diels-Alder. Now, I don't know about you guys, but I don't really see a Diels-Alder in here, right? Because Diels-Alder would require a cyclohexene. So I'm going to guess that this is some kind of Robinson annulation. But remember, Robinson requires a double bond, right? It's a cyclohexenone. So it's something like this. So if I had to guess where this pi bond went, I mean, I probably lost it in like a hydrogen. Yeah, I'm sorry, I dropped the microphone again. I need to get some really good sleep tonight. But if I had to guess where this alkene was lost in this hydrogenation event, right? I'd probably guess where this ketone used to be, right? Because if I'm doing like a Robinson annulation, right? What I'm doing is I'm adding a Michael acceptor at some position, whether here or here. I mean, you can kind of see where, right? Because clearly we're functionalizing this carbon. So that's where the Michael acceptor went, right? And so if it's going to attack on the carbonyl, and that's going to turn into an alkene, right? So if we're losing a carbonyl in an aldol type reaction, it's probably going to be, that's probably where the alkene's going to show up, or I mean, it's where it's going to show up. And so I'm going to go ahead and guess the alkene was here. I don't really need to guess. I'm pretty confident in that. So now I can do my alpha beta cut, right? Alpha beta, where oops, sorry, let's do this. Getting ahead of myself. Just want this to be done with. Okay, where again, alpha stays the same, beta, we add a carbonyl. And then again, we get our 1,5 carbonyl, where you can ask yourself, I mean, you don't have to ask yourself, you can see where it's being added. It's clearly being added here. So this new chain here, that just used to, I mean, this is where enone used to be. We're just going to cut that off. So our enone looks like this, R minus. And what we have is this starting diketone. Now, why is it that this diketone deprotonates here and not here or here? Think about this as like a doubly alpha position, right? It's alpha to 2 carbonyls. This is just alpha to 1. So it's doubly acidic when it's next to 2. Okay, cool. This actually has a name, this type of ketone. It's called the Wechsland ketone. Very, very important. If you take 231, you'll learn a lot about that. Cool. All right. Let's actually do something really quickly. The top one's a little bit long, so I just kind of want to get through this. This here, right? I mean, we have a hemiaminal or like an aminal acetal kind of thing going on. Biggest thing here is just to recognize that we have a carbon flanked by these two heteroatoms. It's kind of like an acetal, right? So I can kind of think of like internally thinking of like a hydrolysis here, but heating this up in some acid, right? Probably just get rid of this and this. Right? NH2 and OH, right? Remember that carbon, that's sort of like the acetal carbon. What do we give it? We give it a carbonyl. So we know that we added acetone with heat and acid, right? Got that sort of acetal type thing going on. And then we have that vicinal amino alcohol that I talked about. Really only one target for that, right? It's this guy here, which cyanohydrin comes from aldehyde. Right, this is just PCC. This is just LAH, and there you go. Okay, cool. So that's a pretty cool reaction there. Apologize for just being fast. Again, I wanted to be done in 10 minutes, right? But I probably won't be done for like another 30, which is kind of annoying, but it's okay. It's not annoying. I'm not annoyed at you guys, just annoyed at myself, I guess. Cool. All right. So last reaction, or last synthesis, probably the most insightful out of all the syntheses. This is probably the most insightful one. So definitely please understand this one out of all of them. Cool. Okay, so we have this bromide that's turning into this epoxide. Some things we can do kind of instantly here. Epoxides come from MCPBA. Okay. So I mean, essentially, we're tracing back to an alkene here, and not just any kind of alkene. We're tracing back to a cis alkene. Okay, so if we're tracing back to a cis alkene, you can think to yourself, oh, well, this is a Wittig, right? We're essentially adding 3 carbons to an alkene that's cis. I'm thinking Wittig, so I can go ahead and cut there, right? And say, okay, I added in that whole chain there, but with PPH3. Okay. But once you get to here, you should really stare at this for a second and think about this. You're asking in this step that a Wittig only attack an aldehyde when there is another ketone present. Now, a lot of you guys are probably thinking, well, hold up. You said way earlier, almost 3 hours ago, that aldehydes are more electrophilic than ketones, right? So it shouldn't be to anyone's surprise that the aldehydes attacked. And to some extent, yeah, that's true, right? You can expect that there is more attack on the aldehyde than the ketone, but you never want to run the risk that a reagent has the ability to attack something else, right? This is that whole idea I guess I tried to talk about earlier, but I didn't really talk about, where you might have 2 carbonyls, but you only want one to react, right? This is that point in time, right? This is when we want to employ a protecting group. Jesus, this is getting pretty bad. Dropped it like 4 times then. My bad. I just gotta sit better. Anyways, now if you're not totally convinced that this is a problem, I'll peep you into another problem too. This step is also kind of trash, right? You're asking an alkene to epoxidate in a condition where you might accidentally even esterify or turn your ketone into an ester. So you've got even more of an issue here as well, right? BR2, you might say, oh, just do the BR2 method, but that can still also react with the ketone, right? You could get some kind of alpha reaction there. So generally speaking, if you want to react with one carbonyl on a dark carbonyl compound, you're just going to have to protect. So really the first thing we're going to do here, we're going to go ahead and protect, right, our ketone. You can use either the oxygen acetal, or you can use the sulfur one. It doesn't matter, up to you. I don't really care. Okay, but we'll go ahead and do that. And so that way, throughout this synthesis, so I'm being a little lazy, I'm just going to say that we deprotect after the MCPBA. But that just means that during the synthesis, right, we never have to worry about this ketone ever overreacting or doing anything we don't want to do. Okay. Now, for a fact, no questions asked will always attack here. I have nothing to worry about. Okay. But from now, I mean, bromide to the aldehyde. I mean, aldehydes are going to come from, I can a couple of things, right? You can come from an alkene, right? And you can do like an ozonolysis. It can come from an hydroxide. I think the hydroxide is probably the easiest thing to do here. Just because if you kind of look here, it's just substitution, right? So an SO2 reaction. So hydroxide to PCC, right? PPH3, MCPPA, then deprotect. Okay. So this one is really the important one to kind of show you how in synthesis we might have to protect. And trust me, there might be syntheses where you have to do this. It's not guaranteed, but it's a possibility. And it could just, I mean, this could also just be like a multiple choice question, right? Like if you want to attack, or like if you want to do reactions on dicarbonyl compound, right? Protecting is always just your safest bet, right? That's just always the safest thing you could possibly do. Okay. You can also use the sulfur one. Generally speaking, the sulfur one is a lot more resilient, but because it's more resilient means that it has harsher conditions to take off, right? So that's that whole like mercury chloride condition. Taking it off is a little rough. Okay, but yeah. Cool. So the Acetal is just a bit more resilient. But it at this level in class, it doesn't matter which one you choose. Just choose one of them and use them if you have a dicarbonyl compound. Okay, cool. But again, epoxidation, the cis alkene kind of yells Wittig at you. I don't know what else would. And then just kind of going back, right? Like, oh, okay, that'll cut here. So Wittig, and then the Wittig reaction, you can kind of just put it in there. If you wanted to, I guess you could have also built it. So for those of you that are like, oh, well, what if I wanted to make it? Yeah, you can make it too. So how would we do that? Let's start with bromine. And then you'd have to, I mean, definitely protect or have it protected, right? But you could add in PPH3. Right, plus NBUE. So this is minus. And then from here, right? So 1, 2, 3, 1, 2, 3. So I just want to add in this here as a carbonyl. Oh yeah, that could have worked too, actually. Yeah, that would have worked too. I didn't consider that. Now you're just adding this as the, so in this case, instead of making the aldehyde, you're adding it in, right? Yeah, you could totally do that. And in this case, actually, you definitely have to protect because this N-butene step, if this were a ketone, so let's say that this were still a ketone here, this N-butene step could attack the ketone, right? N-butene is organometallic, can attack the ketone. It can also deprotonate the ketone, right? It could do like an aldol type or you enforce an aldol type reaction. So 100% in the second type of synthesis, you would have to protect. Okay. Yeah, you could totally do this. That works. Right, turn the starting material into the Wittig. Yeah, that totally works. Cool. All right. Well, with that, that's the syntheses. Fucking finally. Let's get into the multiple choice. Not gonna lie to you guys, NMR is looking pretty bad right now. I think I don't want to talk about this one. We'll talk about this one. This one has a little trick in it. But let's go through the multiple choice so we can just get this over with. Like I mentioned, multiple choice 100% is going to be old material. So just be prepared for that. Be ready for that. This is where and remember that all the practices I wrote, I think only 1 or 2 of the questions that I wrote actually showed up on the exam. A lot of those other ones didn't. So you have a lot of multiple choice practice for old material you can go through to figure out. So don't be afraid. One thing I'll tell you is that a lot of Nastiri questions, you can usually boil it down to 2, and then it's the 2 that she wants you to wrestle against. So, if you get really good at calling 50-50s, right, you should be fine. Cool. All right. So first one, dominant resonant form of these molecules called azolene. Okay. For this question in particular, I kind of wrote notes on the MC to kind of show you guys my thoughts. But you kind of see these rings that are conjugated systems. So to some extent, you should be thinking about aromaticity, right? So whichever one of these is the most aromatic, probably the best one. That would be this one here, just because if you kind of isolate this ring, right, that cation is an aromatic cation. So it's looking pretty good. The rest of these don't really have that like isolated cationic ring. Or like isolated like aromatic resonance form. So that's why this is probably the most dominant. And in fact, actually, I think it is, because if you I think I read about this, but this carbon here is actually the nucleophilic carbon, which would suggest if this is nucleophilic, this would have to be cationic, right? Or maybe, possibly, I don't know. I remember reading something like that, but yeah. So this is aromatic. That's why that's this one. This one doesn't have that. This one, I mean, this is anti-aromatic actually, if you look at it. So very, very bad. And then this one, again, anti-aromatic. So 2 of these had anti-aromatic features in them. One of these was just kind of like a dud, right? And then this one is a very, very good one. Cool. All right, vocab. If it's a name, you just got to know it. The electrophile, It's not a bromelain, it's not a halide, it's not a bromide, it's a bromonium. Cool. Rearrangements, remember that's cations. The motifs for this look something like this, right? So you're looking for something like this in your molecule when you form the cation. For this one, the cation's on tertiary, so nope. This one's on secondary with no branching, so nope. And then secondary with no immediate branching. This could potentially rearrange, but definitely won't rearrange the fastest. So I'm not really looking for that like that one. This one, though, without a doubt, the cation, if it forms on this one side, will rearrange practically instantly, right? That's not even a question, not even a doubt. Okay. Cool. Which substituent increases rate of reaction? Right, these are activators, so EDGs. Remember, EDGs kind of what gives them away is they have a lone pair next to the ring. So, I mean, oxygen, lone pair, the ring is on the other side of this. No lone pair, it's a cation, so EWG, right? I mean, cation and cation, so they're EWG, so clearly this one. Okay. I highly recommend going through that list again in your chapter 16 notes, I think. That goes over EDGs, EWGs. Just be very on top of this. Cool. All right. Which intermediate does not form? So fortunately, yes, these kind of questions do exist. They're meant to kind of get you to think through the mechanism, or at least think of concepts of the mechanism, right? Just remember in this particular one, the point was that it's anti-Markovnikov. So your intermediates should kind of echo that. So if I have this as propine, right? Anti-Markovnikov means the intermediates are, for the most part, on the terminal carbon. So terminal, terminal, terminal. This is internal. This has to be the correct answer, right? Because that's definitely not an intermediate. Okay, so you can drop the whole the whole mechanism, or you can just think about concepts in the mechanism. Either way should work, right? But the concepts is what's really going to get you to get this done a lot faster. Cool. All right, next one, most reactive to water. This is just reactivity of carbonyl. Remember, EWG is the most reactive carbonyl. So, I mean, we see that right there. So that's the most reactive, right? If I had to rank these, because you could have a ranking question, this would be 1, right? One of these aldehydes would be 2, probably the less steric one. This is more steric, and then 4 is the ketone. Cool. All right. Hydration products of 2 pentyne. So you need to draw this. So 1, 2, 3, 4, 5. Right. This is asymmetric, so we'll have 2 products for the hydration, one on the 2 carbon, one on the 3 carbon. So these 2 here, so the second and the third. Okay. Tollens test is that metal that I think I mentioned with the OH minus. Remember, that's aldehyde's response to that. So you're looking for an aldehyde here. You can actually get away with this a little bit just by kind of look at the functional groups. I mean, this is a ketone, so it can't be it. Alkyne can't be it. Acetals are masked carbonyls right there. Carbonyls that have been attacked by 2 alcohols to make an ether. Definitely not an aldehyde though, right? They're stable. So definitely not this. It's the hemiacetal. Remember, the hemiacetal can break. So I can kind of break this carbon there, or that bond there, to kind of unveil, or I guess I break here and here, really, right? To kind of unveil a water molecule at OH. And at that carbon that I'm breaking at, right, those 2 oxygens, a carbonyl. Particularly this one's an aldehyde. So hemiacetal, look out for those right there in equilibrium with their cyclic and acyclic forms. Cool. All right, so this one will respond. I made a bit of a typo here. There should have been SO3H, but that's okay. Between the 2 rings, the oxygen donating ring is way more activated than the bromine donating ring, or really deactivated ring. So I can almost even ignore this as a group. I mean, it's a group to be a group. So sulfur will just never show up on there. So the sulfuric acids won't be on the bromine ring. They'll either be in the oxygen ring. But again, if I just kind of ignore this and just treat it as like sort of a big substituent, right? So this is a big substituent. Again, remember, sulfuric acid groups are huge, right? They don't want to be next to other huge things. So consider the size of a methoxy and consider the size of a phenyl. What's larger? That's the trick of the question. right? A lot of people, they think, oh, the director, it's going to go always para to the director. But in reality, that's when it's monosubbed, right? If I have an EDG, of course sulfur is going to go para because the only thing on the ring is the EDG. So the largest thing, the thing it has to combat is that EDG. But if I have two things in the ring, right? So if I have another EDG in the ring, what's going to determine where the sulfuric acid goes is going to be size. This is really small, sulfuric acid will be happier here. This is really large, right? It won't be happy here at all. Definitely will never be happy here though. Okay, so that's the trick of the question. Yes, sulfuric acid likes to be para, but only if that's para to that largest thing possible, right? And so in this case, the largest group is the phenyl group. So that's why it's para to that phenyl group. Cool. All right. And the last one for this one, I mean, if you just go through the reagents for this, it'll make sense. You can kind of see though that we have like an alkylation event on the alcohol O, right? There's an alkylation. So, I mean, as long as you see some kind of like etherification process, so like Williamson ether, that's usually the thing. I will add some visuals on how to think about this. This definitely can't be it because that's an acylation. So we'd have like a carbonyl, like this is, I mean, this is kind of a lot of weird things going on. So probably not the right answer because we have to figure out what to do with the carbonyl. This one here only has HF and the alcohol. So I suppose you could assume that water falls off, but if water falls off, I mean, you form the allylic cation, which can attack either here or here, so it complicates the reaction. I'm not totally confident. Same thing with this guy too, right? AlCl3 will get, pull off the aluminum chloride. So the aluminum chloride will pull off the chloride. So we form this aluminum cation. Again, we don't really know where that oxygen is going to attack. So that gets a little complicated. So what that leaves then is this guy here, which is very straightforward esterification process, right? We'll form that. HF will form the cation at this position. We'll get the attack, right, that we need. The other three methods are just not reliable in that case. Okay, so expect a couple of these reagent transformations. There usually is a step in one of them, and in the wrong ones that kind of like absolutely just like kill the reaction. So just look out for those. Cool. All right. So that's the first set. Let's get the second set of multiple choice. Try to get this done as soon as possible. All right. So I didn't really go through the concepts of this because I just wanted to get the reactions, and I'm happy that I did it because we would have been here another hour. So some concepts in terms of enolates, some things to know. So again, enolates are when we have like an aldehyde, we have a proton, we remove that proton. Okay? But let's say that we have a chiral center, right, at that alpha position. Right, one of the sort of proofs or evidences that these protons are really acidic is that in solution, these guys get deprotonate to form enolates, which are flat sp2 centers, and then they can reprotonate to either reform the original center, which in this case, I think this might be S, I think, I'm not sure. Well, I'm just gonna call it S. Okay, some nerd can that's kind of bullying. I was gonna say some nerd can just correct me, but anyways, but it can also reprotonate to form the other isomer, so like the R isomer. Yeah, that's totally possible. And so racemization in base is experienced by any alpha or any aldehyde or ketone whose alpha carbon is chiral and has a hydrogen. So two requirements: chiral alpha, right? And alpha hydrogen. So that's what you're looking for. So this is neither chiral nor does it have an alpha carbon. Same thing with this. Well, this does have alpha carbons, but it's not chiral. So not going to work. This is not chiral, not going to work. Not chiral, not chiral, not going to work. This is chiral and it has a hydrogen. This will experience racemization in base. Okay, cool. All right. B, We have a phenol, we have an acyl halide. Remember, usually benzenes are really good at attacking acyl halides, especially when there's like a Lewis acid. In this case, though, we have the alcohol on the phenol, better nucleophile than a ring. That's what's going to do the attack. So we get the ester product. Okay. Alcohol dehydration. This is just SN1 cation, carbocation. So fast is going to be carbocation formation. Slow is going to be like slower, like the worst carbocation. So who forms the best cation? This would be secondary. This wouldn't even form a cation at all, actually. That is a typo. This would be a tertiary allylic cation, and this would be a secondary allylic cation. So tertiary allylic wins. Okay, so it's really just a question between these two. Which one would win? Cool. I said the name of this earlier. It says betaine. Betaine. Cool. All right. What's the major product of this? So we have an epoxide that can either open the left side or the right side. I'll tell you what, only one of these sides opens for sure. Which side looks special? If you said it's this side here, I agree with you. There's a name for this. An A word. It's allylic, right? So it's a pi bond. So we have an allylic side here. Interesting. So it's going to open definitely on the left side. So our new carbon chain should be on the left carbon. So not this one, not this one. Okay. It's going to be one of these two. Because we're doing the Markovnikov hydration, we should form a ketone. So it's going to be this here. Okay. If we did the BH3 reaction or R2BH, then you would have formed this one. Cool. All right. This one, most reactive, kind of talked about this. There are some carbonyls that are just more reactive than others, or have a higher hydration constant. This was one of those guys, right? Because of the angle strain. So yeah, we do have an aldehyde, but again, aldehydes are a little bit more equilibrating. Ketones, not so much. Right? Ketones, ketones not so much. Right? But this guy, right, is very special because of its angle strain. Cool. All right. Which species produces least heat? Remember, less heat equals more stability, right? So a lot heat would go no stability. So just looking for stable alkenes here, right? We have a tertiary, secondary, right? This only has 2 alkenes. So, oh, shoot. Okay. So I guess I should have, you know what I should have done here? I should have put an alkyne here. I wasn't thinking, because technically this would produce the least amount of heat, because it has just the less number of bonds. I guess I should have just wrote the most stable system. Yeah, this is my bad. That's what you get for writing exams really early in the morning or really late at night. That's my bad. But I was aiming for stability here. This is the most stable system out of these guys here. So that's what I was looking at. So my bad. Cool. All right. Eliminations, right? Those never went away. And you guys didn't get tested on that. I think midterm 1, you didn't get tested. So expect to get tested on the final on how to do eliminations. Recall that eliminations are beta and they have to be anti. So beta, so that's to be Saturn here, and that's to be anti, so that's to be opposite. Clearly, those are not the opposite. So 2 solutions here. One is that you rotate. So if I have this here, right, you can rotate one of these sides. So for example, I can, let's keep the bromine side the same. I'll just rotate the H to the back because that makes it anti the Br. Doing so will push the ethyl to the plane. So this will go to the plane. And then on the wedge will go the isopropyl. Okay. And now I can do my elimination. And if I kind of just sketch everything out without the bromide and the, sorry, let me try it this way. Yeah, if I kind of sketch everything out without the bromide and the hydrogen, right? You can kind of see how this lays out, right? The pi bond, right? The phenyl is anti to the ethyl. So we're looking for a pi bond down the middle, so it can't be these two, where phenyl is anti to the ethyl, so this here. So that's the answer. So that's one way you can do it. Actually, I'm just gonna advise you guys just do it that way because I'm a little too tired to teach you the other trick, and I'm just gonna do this over with. Cool. All right. Moving on. So practice your eliminations. Last two problems. Okay. Which reaction is slowest with methanol? This is an aromaticity question. Right. All these, if you draw the cations, right? Right. This is going to be a double allylic. This is not allylic. This is aromatic cation. And then this is secondary allyl again. I guess this is double allyl. Okay. So what makes the aromatic so special? On one of your slides, very, very quickly, it is mentioned that aromatic cations are super resistant to substitution because they don't want to break aromaticity. So in fact, aromatic cations are the slowest reacting cations. They form super fast and then they don't react at all because they don't want to lose aromaticity. So in fact, slowest to react is the aromatic. Kind of wild. It's a little bit of a tricky one. You would think that, in fact, it would be like non-aromatic, right? Because it would never form at all. And that is true. But non-aromatic, which never forms, versus aromatic that does form, both don't want to react. So it's kind of funny. Okay. So generally speaking, if you have a aromatic cation that forms in a reaction like this, or the question has to form based on the verbiage, right? This is what we're looking for. The other way to ask this question is pKa, right? To ask you for the pKa of the like which has the lowest or highest pKa. And so that can also, like, pKa just tells you anion. So you're replacing all these with anions to see which one has like the most aromatic, I guess, anion. So it's the other way that's asked. Cool. Last but not least, we have the Diels-Alder. Again, the Diels-Alder use the EWGs to guide you. I know it's not very clear where the alkene is here, but we can see where the EWGs are, those aldehydes. So we can cut those guys out, which would mean that it's the best way to draw this. It would mean that we were using some kind of diene like this. Now, obviously, these pi bonds don't work, so you've got to move them. Right? The way that I had them drawn, this wouldn't work, so I move them like this. And now this does work. This is isobenzofuran. And we have this here. Okay, cool little reaction. Right? You do a Diels-Alder with this, right? Move the electrons in a circle, and you form a benzene ring. Right, so yeah, cool little reaction possible in the final. Cool. All right, and with that, that's the midterm or the finals. Let's just look at this here. Actually, let me just blow up the key. I am not trying to. Sorry, I'm just tired. Yeah. So the trick that I'll teach you guys for this, how do you know this is an enone? Two kind of things. One, in the CNMR, the alkene protons or the alkene carbons for an enone, like a conjugated carbonyl, are always super wide, incredibly wide, especially in the HNMR. You can see the protons are super wide. So look out for this pattern. I hope that it's an enone on your actual exam, just because, I mean, it's relevant to the material. And that's what it usually ends up being. So look out for that. The other one, what was it? I mean, actually, hold up. Let's, so how do I get partial here? So CC alkene, 200 is the ketone. Remember, if it's an aldehyde, there's an H at 9 or 10, but that wasn't the case. So that's why we didn't see it. So we'll have a ketone, we'll have an alkene. So how we draw those in, it probably gets you like a point on those, point on that. Get the enone, probably gets you a point, right? Because it's like, oh yeah. And then we have the, the group over here, the highest has to be, usually when it's around here, it's usually next to oxygen, right? So I know it's next to oxygen. Yeah, I mean, that's about it, right? And then next to carbonyl, like this was pretty straightforward. So I guess most of you could have probably accidentally gotten this right, just looking at the values and kind of, guessing where it has to be next to, where it couldn't be next to, stuff like that. Cool. The other one. Oh, I forgot I drew those, the faces. That's kind of funny. What did I do last night? Yeah, I did do the protections. And then, yeah. Oh, I guess these two should be switched, actually. I don't know why I didn't. I don't know why I did that. I did this. I don't know why I did this way. That's my bad. Yeah, these two should be switched. I think I just oh, I guess that was the easiest thing to, yeah, I guess that was just the easiest thing to figure out. But yeah, cool. Damn, this one's why did I write this one again? I don't even remember. Dying algae. I think it maybe because I think Helix did this last quarter. Anyways, yeah, this splitting pattern here is pretty dying. Just a bunch of H's. I mean, there's 4 of them, right, in the 6 to 8 region. It's not aromatic, so you know, I mean, it's alkenish, but it's not aromatic. So you know, this has to be all alkene protons. There's 4 of them, so that's why I guess dying is relevant to chapter 14. So that's what I would recommend there. Again, it's next to 2H, so it had to be, you knew it had to be next to oxygen at least. But the fact that it's a singlet tells you it's sandwiched between two EWGs, right? Because what else could it be next to if it's so high up, right? At 5, and you know it's a singlet, it's got to be sandwiched between 2 EWGs. And then this is probably just next to oxygen by its own, right? Stuff like that. Cool. All right. Well, if you can't already tell, I'm kind of tired, and you guys probably are too. So, good luck. I wish you guys the best. You know, I know it was a rough quarter for a lot of you, especially I mean, you transition from the worst to the worst. Right? So it's like, who likes doing that? But just do your best. It's a lot of material. Don't worry if things don't go well. There's always another chance. Yeah, cool. So just get your last minute questions in. I will definitely work on getting those extra. I mean, I'm not gonna do it tonight. I thought I could, but this took way too long. 3.5 hours. I didn't think it was gonna take this long. So I will within the day write up those extra things that I talked about and throw them on a document. In the meantime, I'll send the worksheet that I talked about that I have with all those extra problems and the answers to them, so that there's not like those will probably cover whatever I talked about anyways. Yeah, cool. All right. Well, good luck, guys. You have a good one. See ya. Goodbye.